Okay, so we will be studying operating system for now. Uh, we will be looking at complete operating system except the scheduling part. Okay, we will not be covering the disk scheduling. Other than that, we are covering everything required for placement and all because my placements are coming up. So first, operating system. We know operating system is the most used softwares popular OS options we have. Popular OS, we have Windows, Mac, Linux, Unix, Android, iOS. Most of the laptops are driven by Windows and Macs, and most of the servers are powered by Linux. Okay. We can write this point here. Linux, Linux. Okay, sorry. Servers are powered by Linux. Unix is one of the earliest and popular OS. So we will see the timeline. Okay, timeline Unix. Mac and Linux. Yeah, Linux are inspired by Unix. Okay, the core kernel of Linux is actually a Unix-like system. Kernel. It's okay. For DRM, what we just put in production part. Linux often would vary. Okay, related to open source, you can find its data point later. The kernel of Android is yeah, is Linux Linux. So, and Android kernel. If we are writing something into files, we can really do it using like okay. What does Earth do? Okay, so we have seen like what we did. Now we can see what does Earth do. The OS resource resource CPU. Okay, arithmetic and logically. So CPU in the C clearly controlling arithmetic and logical. Okay, so this CPU, what do you do? It controls the timing of signals to perform the task. And this do also it does sequencing and execution of micro operations. Okay, written it here. So say run execution of micro operations. Okay. Uh, Now we can see here. This one we can continue. So it is also used for secretion and communication of micro operations like CPU operations. Okay. And yeah, this is basically how CPU is used. Okay. The CPU reads data from RAM effectively. It takes input from keyboard and executes something. Okay. CPU reads data from RAM effectively. So we can write here. Maybe the RAM. Okay. CPU does not talk to these, rather CPU talks to all of these variables. Okay. I guess let's do extend this CPU. Mm, I know. If you please click one, two, three, 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 two, two, one, one, yeah. Well, this is the whole thing. Right? Mhm. Uh, This is the whole fundamental of CPU. Now we should know about resources. Okay. So when we talk about CPU and OS, we talk about how OS effectively manages resources, and those resources are multiple things like RAM and also performing operations effectively using algorithms. Okay, so first we need to know about what are the resources we have. So we have hardware resource. Okay, so we have hardware resources. Just a second. Hardware resources, and we have similarly software resources. Okay, so we have hardware resources and we have software resources. Hardware resources consist of keyboard, mouse, but main thing is CPU RAM. So these are also hardware resources, of course. RAM is hardware. Now also we have software resources. These consist of pipes, signals, monitors, scene. Okay. So semaphores and pipe signals, semaphores. We will not study this. Okay. So I have this diagram over here which will help you understand how things connect. Okay. So we the users first communicate with user OS interface. Okay. Then that communicates to OS kernel. Then that communicates to hardware. Okay. And it can be done using command interpreter. Like in initial days, we don't have any screen. We just had the power cell or not power cell, even terminal. Okay. CMD command prompt. We only had that screen. We don't used to have these GUI. This is graphical user interface. Okay. Command interpreter. And this is cell, which is CMD. Okay. Or GUI. And yeah. So these are use hardware. Okay. So this is how we talk. Now operating system provides convenience to this. Okay. Users of the operating system OS wants to use all the resources very effectively. Yeah, we know. Yeah, operating system provides convenience to the users of operating system. OS wants to use all resources very effectively. Operating system provides a bunch of functionalities to the software engineer to simplify application development. Okay, so mostly operating system are just piece of software written in C and C++, you can say. Yeah, what we are going to these things. Yeah, we will be leaving this file system and device system. Okay, we will be only studying process management, deadlocks, threads, scheduling, and memory management. Okay, so let me write what to study. One, process management, which consists of parts like scheduling, IPC, synchronization, concurrency, deadlocks, threads. Okay, so we are going to study these things. And second, we will be studying so we, yeah, so we will be studying RAM organization. By the way, most probably I will say this because we don't need to know the how RAM is created. Okay, we just need to know algorithms and simply we can cover it. Other parts are from computer organization, like this part is from computer organization and architecture. Not it is solely of OS, but yeah, a little bit we are going to see. And then techniques to manage the RAM, Memory basically here means RAM. Okay, so memory is nothing. I guess I should write memory slash RAM. Okay. Techniques, and then we will be studying virtual memory. Okay. So these are the things that we are going to study. First of all, what is John Newman architecture and history of this? Okay. So Newman architecture we need to know. Newman. Yeah. Okay. So what is it? He first of all, John von Neumann was the greatest mathematician, the greatest, not the greatest, but yeah, one of the great mathematicians. Computer scientist who came up with a simple and elegant architecture of what computers. Yeah, so basically it is stored program concept. The stored program concept. The stored program concept says that any program that we want to execute will be stored in RAM. So what is this? Any program we want to execute will be stored in RAM. So yeah, this is the only thing that Neumann architecture says. Yeah. Okay. So this is the stored program concept that any program we want to execute will be stored in RAM. Okay. The stored program concept says that program we want to execute will be stored in RAM. A program is a sequence of instructions. Okay. So first of all, what is a program? And you can type it like this. We are saying program, but what is a program? Okay. Program is the set in actions that are there in C. Yeah, okay. So this is program. It is a set of instructions. Okay. The CPU read the instructions from memory and execute one by one. So we can write it execute one by one. Hmm? CPU also reads the instruction from here from the RAM. That is why it is called a stored RAM. It's a instruction RAM and executes one by one. Suppose, okay. Now, as I told you that CPU is this control unit and arithmetic unit, and it is memory unit. memory. These things go to these things come from memory unit and input output is there. Okay. So CPU doesn't take input directly, I told you. It takes input from RAM. So this input comes, this uh, goes actually here. Then from here the processing happens and then output. Okay. So this is how the things run. Uh, I can paste the diagram here also. And it's also considered the definition, that's why it is. So yes, I got you. So this is the thing. Now, as we said, this was John Newman architecture, and John Newman gave this concept in 1940s, and it was revolutionary back then. The CPU, there are also other components like registers. Okay, so yeah, registers. You need to remember registers are the fastest memory. Like the transfer happens between from register to register is very fast. So first, let's read this. This is not too much big of a thing. Okay, this is just introduction. The main thing will come later. Okay, so introduction part is pretty easy. So at this secondary memory, yeah. So the program, whatever code we write, uh, it is stored in the like our HDD or SSD memory, whatever we have computer have. Okay, that is also called the secondary memory. The ROM. Okay, RAM and ROM. We know two types of memories are there: read-only memory and random access memories. Read-only memory saves the file in hard disk. Uh, it consists of C program. Then it is compiled in machine level language. Okay. So this is how things work in RAM. Primary memory, we have set of instructions I1, I2, I3, and it is performed serial wise. Okay. Currently, we are seeing that it is performed serial wise. Later, we will see how it happens. Okay. Why all programs run after it comes in primary memory? Why CPU cannot execute directly from hard disk? Okay. I had this doubt that why all programs have to come to RAM and cannot run from hard disk directly. Because the speed of secondary memory is lower than CPU and the speed of primary memory equals to CPU speed. Okay, this is the core reason why it happens in primary memory and not in secondary memory. The sequence of instructions is specific to microprocessor is stored in the RAM. Okay, so whatever instructions are there is specific to microprocessor is stored in RAM. Now comes the instruction cycle. Okay. So input occurs, process data, stored variable. Okay. So you can consider an example how instruction cycle happens. Um, in CPU we have control unit, arithmetic unit, and registers. We also saw here that we have memory unit. Okay. So we have registers. Input goes here. The input register stores the input, and then the inputs get processed using the CU and ALU, control unit and arithmetic logical unit. Okay, and then output occurs. And this happens between RAM because RAM communicates with CPU. It stores and the input also taken by RAM and output also taken by RAM. Okay, so basically this is how the instruction cycle works. Registered like this, we can store variable in the registers. So this is a R1, R2 are registered. This is memory and whole memory. These are parts, different parts, and this is register. You can store values of variable register. Okay. A register is basically a bunch of memory which is part of CPU chip itself. Okay, it is not part of RAM. We must know RAM is different and registers is different. Registers are part of CPU. Like these will be performing operations, but how will it store those things which it have to perform? It cannot directly fetch from RAM every time and just do it. It will take time. So we give some very fast memory registers associated with the CPU. And this CPU and this registers job is to store the small part of instruction and uh, perform operations on it like CU and ALU and output the result to the RAM, and that's RAM will can give out. Okay. This part of CPU, therefore it is much faster to read data from registers when compared to reading data from the RAM. Yeah, I told you. It is not part of RAM because it is faster than RAM. How does CPU execute a bunch of instructions? That is what explained by instruction set. So I should write here that the next topic we are studying is instruction cycle. Okay. Then I will add this diagram of instruction cycle. RAM is basically a sequence of addresses. We can store data in RAM and we can access them using addresses. In C programming, we use AND or ampersand to get the address of a variable. Yeah, you know this. Right? We use and ampersand and also pointers to get a specific value. It's this one give the address and pointer gives the value. This is that is basic C. So RAM consists of instructions like 100, 101, and these instructions may have like add two numbers 120 and 121. So this 120 gets stored in one register and 121 gets stored in another register. And then what is the instruction of them? This will be performed by ALU. ALU will do what? It will add both of the numbers and then it will return those numbers to RAM, and then we can RAM can say this instruction has been performed and it can go to next instruction. Okay. So yeah, these were registered and we saw here PCM, ARM, DRCIR. These are what their definitions are. Memory address register, memory data register, current instruction register, program counter. There are different types of parts of registers. Okay. So how does OS work? Like we have this C code, A plus B compiler converts to micro instructions. Yeah. So this is one instruction. It is converted to micro instruction. Load B inside R1 register 1, load C inside R2 register 2, add R1 and R2, stored A in R1. Okay. Full unit is responsible for sequential execution of microinstruction. Okay, so this was the whole thing. This is not tough, I guess. This diagram is good, I guess I should. And this example is also good. Okay. I will write here how it works by the way. Execute cycle, execute cycle, the history of operating system. Yeah, we will soon begin now with our core topics like multi-programming, multitasking. Okay, so this is just a small part. Now let me write some clarifications here so we cannot have any doubt. Registers are different than than register is a very fast and small body associated with CPU to do micro instructions and data. This micro sun get by okay. So this is the whole story of register and CPU, and this is the instruction cycle. Addressing PC copied to MAR, PC implemented to next instruction, described by MAR, and this is the whole working of CPU. Now this is just an example of its work. I have explained it. Okay, so here we see we don't have any proper definition for interrupt, but we can understand this. Okay, so first of all, to understand interrupt, let's take this example. We have main int I int j consists of three. Int j equals to j into 2. Then we take input of I. Then I is divided by j. Then we print. So these are all lines. These are set of instructions. These are then converted to machine level instructions. Okay. Uh, then in RAM we stored I and j that is taken from the keyboard. Okay. J is already predefined 5, but I is not because I need to be taken from the user. Okay. So 9, 2, 3, and 4 gets executed. Okay. It does not require any input. Okay. So let's note that each of 9, 2, 3, and 4 will individually form into multiple instructions. I mean, instructions before they get executed. Okay. It is not like all three will be performed simultaneously. This will be performed separately. This will be performed separately. This will be performed separately. Okay. Now comes the interesting part. Line 5 tells CPU and ALU that we have to wait for the input fulfillment. The This becomes either idle as it waits for input. This creates an interrupt. Okay, so this is an interrupt. That is, our sequence gets broken due to some uh, interrupting thing. Like here, it is taking input from user. Interrupt is basically interrupting the flow here, and we are expecting some input to our idle system. Okay. Therefore, the flow of execution has been interrupted, waiting for something external to the CPU. Say user input 5, therefore 5 gets copied, then all will get executed. 9 7 has to print to the monitor. But even here we can have interrupts. Say there are a lot of things that we are getting printed on the monitor right now. Till the time 9 7 is printing on the monitor, we want to wait. There can also be cases where outputs don't create interrupt. Okay, like if we don't have anything to output, then we can simply print this. This is the, I guess, best example of interrupt that you can find. Fine, okay. So, yeah, I'm not going to here write the whole paragraph. I will just write interrupts. So, I guess I saw that a good one. Interrupting. No execution of inputs. Instruction, actually not instruction. You, uh, expecting to receive input from user in possible including print or to not necessary. Okay. So we have studied till now the history of operating system we don't need it much. Yeah. So we can now move to our uh, core OS things. Okay. So like uniprogramming versus multi-programming, multi-programming versus multitasking, preemptive versus non. Okay, so now types of multi-programming, single user versus multiple user, preemptive, non-preemptive, preemption. Now the modes of CPU execution, fork. Then we have solved problems. Yeah, then process management comes. So it is not too much far away process management. Then we'll see processes, then process states, queues, scheduling, swap space, scheduling queues, so ready queue, block queue, device queue, schedulers and dispatchers, and then throughput, wait time, IO burst time. Yeah, then we will have algorithms also, CFS and all. So yeah, it is not too much. First, let's begin with uniprogramming versus multi-programming. Mm, yeah. So in uniprogramming versus multi-programming. Okay. So let's discuss first the uniprogramming. And here we multi. So uniprogramming the ability of OS to hold a single program in so first read uniprogramming one program is executed at a time. It is huge wastage of resources like this. Okay. So consider if you are only executing one instruction at a time or one program at a time, then if CPU has there are multiple CPUs, okay, then that will be a wastage of resources because we are only executing one program. And consider if that program is just in an interrupt, like waiting for a user, then no other programs can run during that time. That's why this uniprogramming is a bad thing. Okay, suppose CPU is executing a program at instruction, the program P1 goes interrupted and is waiting for some keyboard. In any programming environment, CPU is still running P1 and program P2 waiting to get CPU. Okay, so this was the thing. Many programming your devices CPU that's system to operate and therefore less throughput this efficiency. So we can write here it is one. And in multi-programming, even in multi-programming, one program handles CPU. Mm. The whole idea of multi-programming is we can increase the efficiency by having multiple programs executed simultaneously. In multi-programming, the RAM will have multiple programs and CPU will be allocated to another program when the currently running program gets blocked. Okay. Mm. Why then? Mm. We become idle. CPU will run another program into the initial program we get related to. Yeah. So this is the difference between the unit programming and multiple programming. So yeah, the shift of unit programming to multi programming happened in the previous side of planning on the first of planning difference. Now what is multi-programming and multitasking? Okay. Yes. Okay. Two types of multi-programming. Okay. Mm, two types of multi-programming are there. So we go. Now what is the difference between single user and multi-user? So single user, your PC. Only you use resource, no one else. Multiple user using same resources like in environment. Obviously not some users. Okay. In Linux server, it is a Unix server, multiple users can simultaneously log in and use it. So basically simple. Maybe I should write the definition here somewhere. Now preemptive versus non-preemptive. So what is preemptive? I don't think most of it is to give away control. Yeah. So preemptive is nothing but is starting in GPU. Basically, the moment Honda with the output input output event go to ready queue, it goes to CPU, then it asks the input output to request, it goes in input output queue, then input output event happens, then again this goes to memory until the task is finished, and if task is finished, then job is terminated. Okay. So this is a good flow diagram of multiclassing OS. Also, preemption is done on at least time and priority. I get why we are considered. We have not even studied the main topics yet. We have not reached to the process management. Okay. So this is a good thing. Okay. Architecture requirement for implementing multi-programming OS. They can destroy devices, DL, compatible. Check support, address transmission. So how does it process one? CPU, logical address. Yeah, so this one's important. We talk here about logical and physical address. Okay. Suppose a program P1 is in the CPU. So it asks logical address to access instruction and data from main memory. Okay. Like the RAM. Then this memory or the one file is formatting the definition of memory correctly. But this converts this logical address to physical address, and this is the actual address in the main memory. And then it mm, fetches the instruction or data from the main memory. Okay, so this is the whole process that happens. You can take an analogy of logical address as someone telling logical address as telling someone directions like 200 meter left of temple, and physical address will be coordinates of the house. Okay, for reaching that place, we need coordinates. So we translate the address from logical to physical. This is done by NVMe. Or why do we need two addresses? With one address physical, each program will directly access physical memory location. A buggy program could overwrite memory used by another program, corrupting data and causing crashes. Logical address prevent this by creating an abstraction layer. Program operates with logical addresses and the OS translates them to physical addresses, ensuring programs don't interfere with each other's memory space. Okay, so this is why two addresses were required. Now pre-process. Okay, so what are the requirements for implementing multi-program? First, secondary storage devices. Memory system should support address transmission, and this was the whole address transmission thing. Then processor CPU. Dual mode operation must be supported, that is user mode and kernel mode. Not every program should get access of kernel. Like suppose if a program is asking for uh, certain memory location or certain resources that should not be accessible to them. Those are kernel mode operations. Okay, and user mode operation means like it is controlled basically what we want to give. But kernel mode is gives the program access to the operating system and its resources. Okay, so processor or CPU must have both supported so that a buggy program could not crash the OS. This is again due to the same security issues. Okay, so yeah, user 1 and kernel 0. Okay, so these are denoted. User mode is preemptive. It can run user application, non-privileged mode. Okay, and kernel mode is non-preemptive. It is privileged mode and routine programs. The whole operating system programs like suppose anything. If we uh, touch anything like this is or change any settings, whatever, those are kernel level programs and those are non-preemptive. That must happen, otherwise the OS can crash. Okay, so we cannot block the required instructions. That's why it is also called privileged mode and it is done on routine programs. Okay, it is atomic, it is non-atomic. The 0 and 1 symbolizes in which mode we are in. Okay, this is nothing but the mode we are in. There is a register in CPU named PSW, processor status word, which stores if the mode bit is 0 or 1. Many times it becomes necessary to switch mode, that is user to kernel or kernel to user. We'll study about mode here. Okay. So it is not that tough. Okay. We have studied about interrupt before, so it will not be a hard thing to do. Okay. So yeah, we understood this thing. Now let's read this example. If some user application were to avail OS kernel services, then mode shifting is must. Okay. If someone wants to use the kernel services, then mode shifting is required. This is mode abstract. This is less abstract because here we show everything, but here it is users don't see the abstraction. Okay. Like users don't see the behind the scene things, how everything works. Okay. And it should not be even visible to them due to security issues. So user system programs, application programs, user programs, library routine, and from here we enter the kernel mode. These are parts of routine modes. Here we enter kernel mode. System calls, operating system, and computer hardware. This is kernel mode. Okay, so this is an important page for revision purpose. We should actually add this in our notes. Okay, so now let's study the modes of CPU execution or fork. So there are two modes of execution, user mode and the kernel mode. The kernel of an OS is basically the core piece of, how many pages do we have completed till now, by the way? Okay, 18. Many to go. There are two modes of execution, user mode and kernel mode. The kernel of an OS is basically the core piece of the software which enables the OS. Okay. So kernel of an OS is basically the core piece of software which enables the OS. Every user submitted in runs in user mode. In a user mode, preemption is possible. So we should write here what is kernel mode. I think the quality is too low. We should not add the whole page. Okay, let's add it in chunks. Okay, let me stop that. Okay, so yeah, I have added the page in here, and now I can write in kernel mode as privileged mode and how privileged, a core piece of software which enables the OS. Okay, so every user given program runs in the user mode. In a user mode, preemption is possible. In kernel mode, most of key functionality runs. If a sequence of instruction cannot preempted, then such a sequence of instructions are said to run in atomic fashion under atomic. Okay. Most of key functionalities are done. So it is non-preemptive. A sequence of instruction cannot be preempted. Okay, so what is atomic? We saw here atomic. Yeah, atomic, which cannot be preempted. Okay, so atomic is the thing which cannot be preempted. No debate in process status. What we saw that above. Now implementation of mode shifting via API and SCI. So yeah, fork is a thing. Fork is a kernel mode thing. It creates child process of parent process. Okay. Node is compiled and transferred to SVC supervisory called BSA branch and save address. So mode shifting is done via API and SCI. API is application program interface which tells what OS service we can avail, and SCI is system call interface. It is non-privileged instruction. These are, and fork is privileged instruction. We declared three variables in the memory. We have basis of A, B, and C. Execution of forks results in creation of child processes. Okay, it is defined in OS kernel. It is an OS routine. Okay, so fork is often called a system call or syscall. The function is declared in unistandard.h, unistd.h. It is this function eventually calls the OS. Fork creates new process. It copies the instruction and variables while executing line 3. Fork the OS takes control and it goes to kernel. Okay, so while executing uh, the instruction, OS take control and goes to kernel and takes the instruction memory and creates a copy child process, and the control is transferred to child process, and child process execution begins on whatever is there after the fork. After finishing the execution of program, the control is transferred back to the parent process line after. Okay. So I know you have not understand. We will understand this by an example. So this is a function P1, fork, and print. Okay. So this first fork call will create a child process. Okay, one. Now this second fork will create another child process, two. Now this print will send it back to this print, and this print will send it back to this print. Now this fork will come, this will open this, and yeah, so it will go to this, and after this instruction it will go to this print and this again print. So how many print statements will be shown on the uh, screen? 4. Okay, so it is a formula 2 to the power n. Okay, the child prints high, and then control is transferred back to parent process. The parent prints high. Okay, so we see first the child process happens, then this parent process will happen. Okay, so this high will first print, then this high will print, then this high will print, then this high will print. Okay, and then back again this file input. Okay, so yeah, no, it will send this to this function, not this I statement. Okay, so it will send it to this function, this for. Okay, and then this for will be. This is the best way to understand how fork statements work. So we can tick mark here, and this is a basic program. It can be asked anywhere. Okay. Now for two forks, two square. Okay. If id equals to 0, okay, so id equals to 4. Okay. If id is 0, then what is id? It means uh, kernel process. Okay. We know that kernel is denoted by 0. So if id is 0, then it will be executed by child process because kernel takes over. Otherwise, if it is not 0, then simply execute this. It will be executed by parent process. And if id is not equals to 0, okay, then it is an error because it means fork didn't happen because neither child nor parent process will run. And p error is nothing but it prints the error. Okay, let the process id of process be here and the process id of child process be here. The variable id in the parent process gets the same value from returned by the child process. The variable id in the parent process gets value from value returned by the fork. Okay, so the variable id in the parent process get the same value returned by the fork. Basically, the process id of the child is updated in the variable. So this is not the big thing. Just remember from here that every process is associated by a process id PID. You can use this. I have used personally this in a project. So yeah, uh, during projects you can take use of the thing that every process is associated with its unique process ID. Okay. And leave this. Okay. So now we have talked about interrupts. We can see the interrupts in depth also. Now solve program, and then we will come to the process management. From here, our algorithms will start. So yeah, we have covered 1/10 of our chapter till now. 9 more to go. But from now, I guess it will be easier to understand because basically you must know that we are doing this for division purpose, not for understanding purpose. Okay. Yeah, basically we can write here kernel mode versus user mode and fork. So, so this is the best thing to understand kernel mode versus user mode. Okay. Okay, so now let's start the process management. One of the two topics that we are going to study is process management and second is memory management. Okay. So process management, what is a process? First of all, what is a process? Process is a list of instruction. Okay. Program versus process. So what is process? A high level code, mm, which is then converted to .exe after compilation, and .exe contains a list of instruction that it is named executables. Okay. So this code is gets converted to .exe, which is list of instructions that we have to perform, and that is what is named executables. Okay. So it is stored in hard disk and in memory. Until it is in hard disk, it is program, and then it is in main memory, it is process. Okay. So if currently you are not opening the .exe file, then it is a program like any software. Like if I can show you, uh, yeah, you can see here .exe. It is not opened. It is currently in the hard disk, so it is a program. But when we will open it, like currently I am opening this Drawbot software, so it is open, so it is in the main memory, and I can show you it is in main memory. If you will open this, you will see here Drawbot. Yeah, Drawbot, and it is taking some memory, 581.8 MB. So it is taking my RAM. This is not the hard disk, it is RAM. Okay, it is taking 581 MB RAM. So currently it is a process. Okay, so process is just an instance of program. So program is data variable. Program can be anything, a data variable or instructions like load, add, store. Okay, so it can be anything, and when it is done, then it becomes a process. So a process is a program under execution. Yeah, we can make our small notes here. This is program versus process. So I guess this is the best definition that we can get of program versus process. Then we can write here okay. So it is similar to that what we studied, multitasking and multi-programming. Both are same things, just it was a Windows version and it is just the program under execution. Okay. A program after it is compiled and stored on this. A process is stored in main memory and resources are allocated to it. Okay. Single program could create multiple processes using fork or spawn. Okay. A process is basically a unit of execution. The program is passive entity as it is not being executed. It is sitting on the disk. When the program is loaded from disk uh, to memory for execution. Okay. So yeah, we see uh, we have initially declared the array, but then took the value of its size. Okay, so it is not valid in C. This is C language, but this is allowed in C++. Yeah, it is called vectors in C++, by the way. So this is a dynamic memory allocation, and this is also a dynamic array. So this term is called activation record. Activation records a function created on the. Yeah, I don't think we need this. Okay, so we can start from here. Process in memory. So this is the whole structure of process: instruction, machine level, static, dynamic, runtime stack. Okay. So initially it is instruction. Uh, then it has. Okay. So process. What are the components of process? So it has instructions. It has statics like variables or constant. It is dynamic like heap, and it is also runtime stack like recursion or function calls. Structure of process in the RAM. This is the structure of a process in the RAM. Four parts of the process. This is important thing. And this is also important. Operations performed on a process. So we can perform create operation, schedule operation, block operation, and suspend operation. So create process gets created, allocate resources, device initialized, schedule on CPU, the act of selecting process to run on CPU, lock input output, system calls, and suspend. Okay. So these are the operations performed on a process: create, schedule, lock, or suspend. Process gets created, process gets scheduled, when to run the process. Okay. Process gets locked due to input and output. Like we learned about interruption, the block is same thing, and process is suspended. That is, process is removed from RAM and stored temporarily into disk swap space. Okay, and resume also starts scheduling when it's time to run the process. Okay, so and terminate when process ends. During resume, we move process from disk to RAM. Okay. Also, the attributes associated with the process PID. I told you PID is process ID associated with it. Also, parent PID is associated with it, and group ID is also associated with it. Like if multiple process occurs together, then there will be a group that will be called a group, and the group ID will be assigned. Then CPU related like program counter, we saw this. program counter registers. Okay, priority is nothing but level of importance. Hmm. Then memory related like memory limits, page tables, file related, file IDs, list of operations. Okay, so this is not a difficult thing. We just need to know everything and learn. So let's learn. Okay, so what are the things present in process? So we can write here. First of all, structure of process. What it contains? First of all, it will contains instructions, then static, then dynamic, then time stack. Okay. So instructions will be like we know instructions, variables, malloc, alloc. Okay. So these are the things present. Also, we should write this as not this, but this as stack. And what was it? This was a stack. And what is this? This will be heap. And runtime stack is also a stack. Okay. So this is also a stack. Okay. And now we will what we will have operations performed on a process. Okay. So let's try to do it into ourselves without C operations. So first will be create create operation. Second will be try to remember. Okay, so let's see. Create, schedule, block, suspend, resume, and terminate. Create, schedule, block, suspend, resume, and six will be terminate. Okay. Now fourth will be what? Attributes associated with the process. So what are the attributes associated with the process? First is process identification, that is PID, PPID, or GPID. Okay. Second is CPU related like program counter registers. Okay. Third is memory related like page tables. Okay. So page tables we are going to study later. Memory limits and all. Okay. And file related like that is file ID. So process contains these things. Input output related, list of open devices. Okay. And protection related. All of these above attributes are stored in table called PCB, process control block. Every process has a PCB. Which is a big lookup table. PCB is also called as process descriptor. This is not tough, but yeah, we can forget what are the things that is included in this. That's why I guess we should copy paste it there. But no, we are doing it for division purpose. So what are the things? Process identification, CPU related, memory limited, related, file related, input output related, or protection related. So only first is process and otherwise everything is related, and which is memory related, CPU related, file related, input output related, and protection related. Okay. So attributes associated with the process. Process related. Okay. So there's the identification to memory related, three CPU related, four file related, five input output related, and six protection related. Okay. So these are the attributes associated with a process. And all of these stored in a big lookup table data structure called. Okay. So yeah. So next we can this context is the content of the PCB. Next is process states, queues, and schedulers. Okay, so there are two types of state diagrams you will see, that is three state diagram and five state diagram. And terminated state, are not counted in number of states. Okay, so we have seen the process states, that is ready, running, terminated block, wait, suspend block. Okay. This is the whole explanation of how process happens. Okay. So scheduling to queues, ready queue, block queue, device queue, event queue. Scheduling to queue, ready queue, block queue, and two types of block queue, device queue and event queue. Yeah, then context switching. Around this will cover 2 by 10 part of our chapter. Okay. So we are currently very behind. Okay. So we are on this. This is, I guess, 30th way. Okay, no, 31st. Very more to go. So yeah, let's continue with our process states. So two types of process states diagram. Okay, diagram. So what are we considering? Ready, running, slash, wait. Okay. So these are the three things we're considering here. What are we considering? Ready, run, block, wait, ready, suspend. Okay. So all options except suspend, ready, and suspend states. These are the two extra states in five-state diagram. Now, how is the diagram looks like? Okay. It is clear noted that new state and terminated states are not counted at the number of states. Okay. Yeah. So it is creation and termination is not considered as process state diagram because it is entering in main memory and it is exiting from. So let's try to draw the diagram. Okay. If we can draw five-state diagram, we can draw three-state diagram or something. So let's draw the five-state diagram. Five-state diagram. First of all, new process is created. it goes to ready queue, ready state, or this is saved in ready queue. Okay, then it uh, runs. It is called dispatch, but to running state, if the process is running, or if it is not, then we can set priority slash timeout. Okay. Now, if it is running, then there will be things like if we need input output, so we send this to IO slash IO calls or sys calls. Okay. So it will be in block wait state. Then it will again go to IO completed. Just completed or IO completed. Okay. Now it also be possible that uh, the process goes to suspension. So it's get suspend to suspend ready. Mm, okay. So yeah, it can go to suspend state from any state, either ready or running, or it can resume also. I guess it is pretty obvious. I don't need to write here. It is resume also. Now from block wait also it can suspend to suspend block. If it suspends during block state, it is called suspend block. If it's suspend during ready or running state, it is called suspend ready. Okay. Okay. Then resume. If IO completed, it goes from suspend block to suspend ready. If the IO completes during its suspend state only, okay, then it will go from this to this. Okay. And after all this, the only thing is completion, that is processes terminated, completed. Okay, this is the whole file. This is the complete five-state diagram. Okay, this is also called process state transition diagram. Okay, So we understood this easily. This is the same story. We can understand this whole thing. Okay. In fact, we should read this whole thing for better understanding. Let me do this in full screen. Initially, the process is new. It gets created, then reaches the ready state. By ready state, we mean the process is now main memory or RAM. The create operation takes on the instruction of the program, assigns on the static variables. Okay. So create operations do this. So yeah, we say the process is new, it's get created, then it reaches the ready state. By ready state, we mean the process is now in main memory or RAM. The create operation takes the all the instructions of program, assigns all the static variables and some space for recursion calls. Okay, and this is the process in RAM itself. Then the process reaches the ready state. So let's understand slowly. So create operations do what? It takes on the instructions of program, create operation, assigns all the static variables and some space for recursion calls. Okay, and do dynamic memory allocation. And this is the process in RAM itself. Then the process reaches the ready states. This is the whole procedure of create state. Takes instructions of the program, assigns all the static variables and some space for recursion calls, dynamic memory allocation, and places the process in RAM itself. The process reaches the ready state. Okay, so uh, we saw the create operation. Then there is a module in the operating system called dispatcher, which takes a process in ready state and moves it to the running state. Okay. So dispatcher takes the process from ready state to running state. Running state means CPU is assigned to the process. Okay. So now everything is in the CPU and the process will be executing. Also, if RAM is running out of memory, like RAM, I saw you. Uh, I have shown you the 581 MB RAM that was getting used due to this robot PDF. So you consider if I have only 581 MB RAM, then the RAM will be out of memory. So the process might have to be suspended by moving it from ready state to suspend ready state. Okay. Then in suspend ready state, the process actually in secondary storage as there is no space in RAM. Okay. So when RAM is out of memory, the process will be sent to suspend ready state. When you suspend ready state, the process will okay. So it is saved in the hard disk rather than RAM. So now while in running state, the process may complete its execution and reach terminated state. So okay, so while in running the process complete its execution and reach terminated state. Resources like memory, CPU are given when the process reaches termination. Okay. So whenever the process completes, then everything like memory, input, output devices, everything gets freed up. Okay. While in running state, the process may have to give up CPU due to priority. In a new higher priority schedule. Okay. So whenever consider two processes are there, in which one process is of higher priority, we will study the priority scheduling method. Okay. So if one of the processes is in higher priority, then the process may have to give up the CPU and it will go to the suspend state. Okay, again. The process may have to give due to timeout where some algorithms in OS tells the process to use CPU for a fixed time limit. And when the process runs out of time, the process is moved to ready state. Okay. So again, when running the process in CPU, the process can get blocked due to an IO call. Okay, so if we want waiting for some input from keyboard, also the running process can get blocked on system call because the child process runs before the parent process. That's why the running process can get blocked. On getting blocked, the process state changes from running to block or wait state. Okay. Now there is one possibility that while running on the CPU, there is high priority process arrive in the ready queue and gets scheduled, but there is no space in RAM. Okay. So when it is uh, running on the CPU, then high priority process gets arrived in ready queue and gets scheduled. Okay. Then consider if there is no space in RAM because the process high priority process is running. Then the process running in the CPU gets suspended to secondary storage and the state becomes suspend running or suspend ready. Okay, not suspend running, suspend ready. And here we saw the suspend uh, suspend ready. We saw there is a suspend block too. Okay, the process is in block wait. It is waiting for completion on a system. When the events are satisfied, the process move from block wait to ready state. There is another possibility that IO may have happened or may not have happened, but there is no space in RAM. Then from block wait state, the process is moved to the suspend block state as the process gets suspended. Okay. Suspend block means the process is in the secondary storage. If memory is available, the process state can change back to block and wait state. Okay. But while in suspend block state, if input output completes, then the state of process changes to suspend ready. Okay. In the suspend ready state, the process is ready to be resumed and given space in RAM. Okay, so in the suspend ready state, the process is ready to be resumed. Now there is one term called swap space. A computer, the hard disk storage which can be used as RAM. Okay, swap space is nothing but hard disk storage which can be used as RAM. A computer has sufficient amount of physical memory, but most of the time we need more. So we swap some memory on disk. Swap space is the space on hard disk, which is the substitute of physical memory. Swap space helps the OS in pretending that it has more RAM than it actually has. The interchange of data between virtual memory and real memory is called swapping. Okay, so this was the whole story of how the process comes and how process gets terminated. Okay, and all the states in between. So now we will study the scheduling queues. There are two types of queues, ready queue or block queue, and block queue is due to two types of queue, device queue or event queues waiting for some input or some event happen. Okay, so queue will be just like a data structure which will store the PIDs, how the process will come. Okay, how the process will, which process will run first. Okay, so it is simple. You will see this diagram, and then yeah, most of our things will be completed. This is again the whole process of how things work. Then we will study dispatcher and context switching. Okay, this is not tough part. The tough part was the states only. Okay, so scheduling queues. I told you there are two types of scheduling queue, ready queue and block queue, ready state and block state. The queue in the ready state is ready queue and the queue in the block state is block queue. Also called device queue. Block queue is also called device queue, but it is a part of device queue because block queue consists of event queue also. Okay. So queues are nothing but a type of linked list. The classification is part of on-memory scheduling queues. Okay. On memory and on disk. Okay, so this is the classification of on memory scheduling queues. Okay. Now scheduling queues are two types, on memory and on disk. Okay. Yeah, I guess I should write this thing, the two classification. Okay. So now what are we studying? Process states and process diagrams. Now sixth is scheduling queues. Scheduling queues, two types. Okay. And this whole classification. Okay, so I guess I should write it like this. I don't know what happening. Ridiculous. I think this should work now just fine. Mm, mm, yeah, on memory and on disk. So it is part of on memory. And here we have on disk. Okay, so this is the classification of scheduling queues. Okay, the process is uniquely identified by its PCB. I have told you, I guess, the PID thing. PID is stored on PCB, so PCB is also unique. Ready queued, queue of PCB which are in ready state. Okay, queue of PCB which are in ready state, ready to be executed. Event queue. An event queue can be anything. It can be a software like completion of execution. Let's start back to device queue, waiting for device. In the processor explode in run and suspend and job queue. Suspend queue has on the process. Okay, so this is part of uh, on disk. Okay, so on disk has suspend queue and job queue. Sus and queue and job queue. Okay, So these are the things which are not present in main memory. And suspend is like suspend queue is stored in second memory. Job queue input queue consists of all the programs waiting to be located in the main memory input process. Process state queuing diagram. Okay, so now we will have this process state and queuing diagram. Then we will see its explanation like we did previously. And yes, we will have the chapter complete of this part, but this portion complete. Process management is too big to be completed. Okay. Now, process state queuing diagram. So suspend, ready queue, job queue, CPU, terminate. Okay. I have written down the numbers on how each thing is working. So first of all, we will come to the job queue. First, we will have job queue. Then the job queue will be loaded to. Yes, I should make it a bit down. Okay. So job queue will be loaded to ready queue. This ready queue will be transferred to CPU in this way. Terminal. Okay. To CPU, but it is not this much easy because it can also happen that from ready queue it goes to suspend queue. Then from suspend queue it goes again back to ready queue. Okay. This is also possible in between. Okay. Now it can also be possible that while it is running on CPU, it goes to block queue because it is waiting for input output. And after it gets input output, it goes again back to ready queue. It is also possible that it does not go to block queue but goes to event queue. Then event occurs instead of IO. Then again it goes to input output. Now it can also be possible that timeout happens. Okay. Again it goes to this. Now it may also be possible that a fork call happens, so a child process runs. Okay, so these are the possible things. Now MTS medium term scheduler, STS short term scheduler, NTS long term scheduler. Okay. The time that each process gets on CPU is quite small, therefore it is called short term scheduler. Okay. The time that each process spends in being in ready queue is quite long, therefore it is for long-term scheduler. The short-term scheduler, CPU scheduler will have some algorithm using which it decides which of the process it will give to CPU. And if any non-completed process exits from CPU, will go back to the ready queue eventually. Okay. If any non-completed process exits from the CPU, non-completed process exits from CPU, it will go back to ready queue eventually. Okay. Now we can move to the next topic, which is, yeah, it is a story about priority scheduling algorithm. From running state, the process can go to terminate state or it could complete the whole process is running. High priority will arrive. Okay, so we know these things. There are two types of suspend queues: suspend ready queue and suspend block queue. We know. Um, I guess we have not written it, but suspend queue is also two types. Suspend ready and suspend block. Suspend block queue. Ready queue. Okay, so this is the whole story. Input output bound process and CPU bound process. It is a good mix of both the CPU. Okay, so there are two types of processes also: input output bound and CPU bound processes. So we have covered a good portion of chapter. Then we will have context switching and dispatcher process preemption. Yeah, then we will arrive to the main topics. After this, we will study the algorithms and all. Scheduling algorithm. Okay, is there anything after scheduling? We got all parts of scheduling algorithm. Yeah, these are all scheduling algorithm, multi-level queue, feedback queue, then a long break. Yeah, then we will arrive to IPC and synchronization. Shared memory, then IPC interprocess communication can happen cooperative and competing. Yeah, producer consumer problem. This from here we will have IPC and synchronization will have interesting topics to study. Okay, so we just have to study two things now, the context switching part and the scheduling algorithm part. Okay, so dispatcher and context switching. So uh, dispatcher and context switching. So dispatcher means controlling of the CPU the process in various systems. So process selected by short terms behavior. Yeah, for dispatching means control of the CPU. The process selected by short terms. The dispatcher does nothing but it leaves control of CPU. The process selected by short terms. Dispatching is nothing but it sends process from dedicated to run. Doesn't matter much of a thing. The process defined by explicitly once process ruling the procedure corresponding to the process they need to destroy. Now the CPU becomes idle. Dispatcher informs the short-term scheduling to the dispatcher and main process. The HTS leaves the main process to be executed on the CPU. The dispatcher completes the process attributes in the PCB into the CPU registers. And the dispatcher leaves control to the control unit of the CPU to start the execution of the process. Yeah. This is a pretty nice experience for stuff. It's for the copy is the process. Yeah, I used to know that it copy the process activates the CDPR and we give the CPU register and the dispatcher gives control to the control unit of the CPU. We start the execution. The process running on CPU requires input of the dispatcher and the realizing such to from running state of the running on CPU requires is the first thing on the completion of process and dispatcher reforms the CPU HPS and HPS in the dispatcher main process and the process to be located on CPU and the PCB from it. We get tributes to the civil and gives it to the civil registers and then dispatcher later. And second one, the process running in city. Whenever the process running on city requires input output, then dispatcher immediately realizes and he goes from running state to block state. Then the dispatcher says PCB and then the final PCB. Now, the dispatcher waits for the HTS, then the HTS reads the main process, and the dispatcher moves the main process into city. Yeah. And it gives more speculative and process. And that's switching decision structure and city. Current execution. Right. So, okay. Right. Process preemption. Then the process is preempted also by the dispatcher. Process preemption can yes, so these are the three things. So on completion of a process, what happens? A process running on CPU requires input and process PMC. So I guess we can dive to the job of dispatcher. and I get academic city one man with five more the the job with the kids study media name maybe I see we can maybe then we can and two what are the second law of expansion second expansion second second law was this is running on security person and this is running one if six and that when that Mm, and we have mm, this is also done by statute. Next, we can study the sequence during time. So, yeah, there are certain properties. Yes, that's and but no, you can so it's during planning the task of SQL system to the process in the beginning and something and possible. You want the best system maximum discipline. It wants to ensure that the process completes their execution as fast as possible. Okay. And right here, that's I get we have we so and yeah, right. So we style. Then there are needs must what happens the task of the cases of the English processing divided is something in the commercial. One is to maximize the supply. Two, eight, listen, zero, really. So this is the main thing. Now there are certain properties associated with it. Firstly, those properties. There are too much like there are 9, 11, 12, 14, 15. Okay, 15 timing sample. Um, Actually, I will try to summarize it using. Okay, let me try to summarize all the timings into solve. Okay, let's do it manually. Okay, let's not use AI during study. Following metrics help to measure the maximum CPU utilization. So first is throughput. It is the amount of work that is completed per unit time. Okay, what we have first is throughput. Second is N by N. Okay, we will write formulas associated with it, not everything. Okay, so formulas associated with it. Like, number of number of process, schedule. Then second comes AT. First process, right? Third we have W time which of process where you live. Okay, this is WT. Now fourth we have PS. got bothered by WT because it command too much expensive to ignore. Yeah. Okay, so yeah, fourth we have DT bus time. Details and some for which process is in termination. Then fifth we have as completion time. Your first rate times in log one. Particularly due to I turnaround DT minus response over the whole response time. Okay. Average time, average DT. Yeah. Then we have weighted TLT. DT minus and the process expands on executing. This is what this now we have they, I don't think they have staying where they don't need s- and so how we define that time instead of writing. So this is different wait time, I guess. Creative means building and schedule is set up in processes. Now we have reached to the final stage of our process, not the final stage, but the second final stage. After this, we just have the IPC and synchronization. So scheduling algorithms. This one's pretty easy. Okay, this one's not the difficult part. This is very easy part. From now on, you will be studying what uh, pure operating system is. Till now, we were just looking at definitions and concepts. Okay, now we will be looking at algorithms, methods, how things works. Okay, so it will be pretty good from now on. Let's wrap everything here. Okay. Okay, so now we will start with our scheduling algorithms. Okay, so in scheduling algorithms, first we will learn about FCFS. This scheduling is nothing but how processes should be scheduled efficiently so that maximum CPU usage happens. Okay, or throughput, maximum throughput. So first we have FCFS. This is the simplest one. First, let us write what number we were before. Yeah, 8. From here, I guess we can start our ninth one, which is scheduling algorithm. And in this, the first algorithm that comes is FCFS. It is non-preemptive and criteria is simple arrival time. Whichever comes first, we will do it. Okay, we will give CPU to that one. So, what are assumptions? One, no IO operation, that is, no block state will be there in this. Okay, and second assumption will be no context switching time. That is, changing the process will not take time. Okay, and this is the table for it, and this is the Gantt chart. This shows the process ID, its arrival time, its burst time. Then it everything. He was, yeah, ST or start time. Okay, ST is start time here, the time at which the process starts. Okay. So it has burst time of this, but then I can show you an example, but this is too naive for the example. Now I will show you the example for the difficult algorithms. Okay, like SJF and SRTF. I will show you example of that. So first is we see FCFS. Here everything is, yeah, start time or scheduling time, whatever. Okay. Let me attach this example and its Gantt chart. Okay, so we don't have any confusion to later think upon. These are the definitions of each term. And this is okay. So this is the whole thing. Now let's read. Scheduling time is the time at which the process is scheduled for the first time. Okay. You can write here also. For when the schedule. Okay. Now FCFS is a non-preemptive scheduling algorithm. That is, once the process starts scheduling, the OS does not preempt it. The OS lets the execution of the process continue till the time the process completes its execution. Okay. So it will let process complete as much time as it takes. Arrival time is the scheduling criteria which our process has the lowest arrival time will be scheduled first. Okay. Similarly, this and this is the example why FCFS is not uh, very efficient, because consider if uh, like process comes too much later and the previous process is has completed fast, then it will obviously there will be a gap between it and we cannot use the processes efficiently. Okay, that's why the scheduling algorithm SJF and SRTF came. So SJF is shortest job first. Okay, so now for the second algorithm we have SJF, which is shortest job first. It is non-preemptive and its criteria is not arrival time but burst time. In how much time it completes the process. Okay, so this is the criteria in SJF. Okay, so the rationale behind SJF is whichever job we can complete first, let's complete that first because it will improve the throughput. Improving throughput is one of the objectives of the scheduler, as we have talked about this. Okay, uh, we can keep this example also. Okay, if new process keeps arriving with very low burst time requirements, high burst time processes like P4 will never get a chance to be executed on the CPU. Thus, it will lead to the starvation problem of P4. It is a major problem this year. Okay, it means if new process will keep arriving with lower burst time, Then higher burst time will perform before lower burst time and it will lead to starvation problem. Okay, because P4, uh, yeah, P4 has higher burst time and we want to complete the lower burst time first. Okay, so we the higher burst time operations will not get a chance to be executed on CPU and it will lead to starvation problem. Okay, it is a major problem in SGF. In case where two processes have same burst time, the tie breaking mechanism will be mentioned. It can be dual process ID or arrival time. Okay, FCFS does not suffer from starvation problem because whichever process comes first will be executed first. It does not need that we are executing these three and then we straight jump to these two leaving this. So it will starve. Okay, due to not getting CPU. Now we will see our first preemptive scheduling algorithm, which is SRTF. It is shortest remaining time first. It is nothing but SJF plus preemption. So instead of only initially checking the burst time and then performing the task, we will keep checking the remaining time from the burst time every second. Okay. Suppose a thing needs to be completed in 8, like its burst time is 8, and another thing has a burst time of 7. Okay. So I guess I have not taken a good example. The good example would be this only. Like consider the first one. Uh, at every unit of time, we have to look at the possibility of a new process came whose remaining time left is less than the current process, and we have to preempt accordingly. Okay, so it is not that we can see. At 0th second, we have only one process which is 1 and its first time is 8. So we uh, put this process in the CPU. Now at one time we see a new process come which is of 6. Then we preempt this, and because this has lesser time, this has now time remaining as 7. Okay, and this has lesser time, so it is 6. Then we will do this. Then we will at second time we see a new process comes P3 which has even low burst time, so we will put this, and similarly we for all processes we will do this. Okay, it is not so tough. Just know that we can break the process in between because it is a preemptive scheduling algorithm. Okay, so it is not that tough. Let me write here. Okay, SRTF could also lead to starvation problem because suppose if a process has higher burst time, then it will never get CPU until all processes comes. Okay, completes. So the same thing is here also. So SDF advantages and disadvantages are this: throughput increases, but average wait time and TAT decreases. but starvation, it leads to starvation. And also, we assume that bus time is known, but we cannot particularly find the bus time, we need to predict it. And how do we predict? Using size of process. If size is more, the process takes more time. Okay, so bus time is nothing but a function of process. It is a very simple methodology, but it doesn't work very well in practice, obviously, because it is not possible. Then, because we can have same amount of size, but we can have different, very complex loops. Imagine if we have machine level language, the number of instruction and amount of memory, all of them may be same between two processes, but one process could have very complex loop and other could have simple loop. In one case, it could loop from intersection 1 to 10, while in the other it can loop from instruction 1 to 1000. Therefore, size itself is not the best predictor. This strategy uh, does not work well in practice, but it is good enough simple approximation. Okay. Second is using type of the process. Okay, so yeah. Second is using type of process. So type of process can be used to approximate the estimated bus time. Like if it is background process, then it will be 12 to 15 seconds. If it is kernel or OS process, it will be 3 to 5 seconds. If it is GUI, then it will be 6 to 8 seconds. Okay, so it is fixed on a table. Then averaging previous CPU burst, like actual estimated will be T1 plus T2 divided by 2. We will check how much it took, how much time it took previously, then we will simply take average of it, and we will get the burst time. And fourth is exponential averaging it. It is also called aging algorithm. So aging algorithm has this formula 2Tn plus 1 minus alpha Tn tau n. Okay. So it will give our next burst time. It is a recursive equation. Okay. So we will get this. So we can write the factors on which. Okay. So these are the four factors. It can be asked in interviews also. Give some factor on which bus time can be estimated, then you can give two or three. Okay. Now these are some more scheduling algorithm, but these are not so important. Okay. if you know how these can be estimated, you can take every day. Okay? You can spend every day. So priority score, it decides which programs are all priority score, preemptive or non-preemptive criteria. Okay. So now we will study the priority-based scheduling algorithm. Then we will have round robin. This is important. Round robin and multi-queue, these are important algorithms. This multi-queue is conceptual. Okay, this is very conceptual. Then yeah, this will get completed, and we will move to our main topic, which is IPC and synchronization. So not too much things left. Okay, so the preemptive or non-preemptive criteria priorities. Okay, so priority based scheduling algorithm. Third, we have fourth, we have priority based scheduling algorithm. Now we scheduling algorithm. Imagine we are reading a web page and we receive a call. Since call has a higher priority, the call will just take over the screen. Okay, so we are the priority score can be static or dynamic. This is just an example of priority score. Okay, so priority score static assigned once and start. It will not change. It has an issue. Static priority can result in starvation, but priority score can uh, change during life cycle of process. We can change the priority the way we want. A dynamic priorities waiting based on priority score. We can write the priority score. There are two types of priority score. Static, dynamic. Okay. Okay, and this is used in Linux and then we can move to our wait. We can paste this example also. Okay. So if we paste that example over here, we get this was fourth. Now we'll study the fifth one. What is the fifth algorithm? But first we see if there is an important. Now and then time taken by dispatcher. Okay. So yeah. Uh, input output burst time and dispatcher time. This is just talking about input output burst time and dispatcher time. And what is aging algorithm? Gradually increase priority of a process the longer it waits. Okay. So we can distinct this thing here. So that was aging algorithm. Now we will study the round robin and multi-queue algorithms. Okay. So round robin and multi-queuing algorithm, there are two types of algorithm. First we will study about round robin. Round robin is nothing but keep the processes run alternatively. Okay. So round robin, it is preemptive. Okay, and for preemptive, non-preemptive, priority-based scheduling if static, then non-preemptive. If dynamic, then preemptive. Okay, and it depends on time quanta we set. Time quanta means decided. No, it's switching, of course. It is also called preemptive FCFS, the multi-programming multi. Okay, so I guess we can paste this part. This is not a good point, but yeah, it can be a good point to say in interview and all. Okay, okay. And this is the example for it. Every process will get fair share of CPU and nothing will get starved. Performance versus time point, a very small, lots of context switching. Yeah, performance is efficiency is low because lots of context switching happens. Small, more context switching. Okay, and large measure context switching. Okay, so it depends on time quanta. If time quanta is very small, efficiency is low. If it is large, efficiency is less. Efficiency is more, but responsiveness could suffer. Or very large, then it will eventually becomes FCFS. Okay. Now, multi-level queuing algorithm is uh, good, but I don't think so. We need it that much. So why not we should keep this because we have learned about good scheduling algorithms already. You will read this sometime later. But yeah, let's try to. Let's we have multiple ready queues, one ready queue corresponding to each process. We have priorities based on the type of process. Okay, so each process will have its ready queue differently. Like operating system will have different, interactive will have different, background will have different, and backup will have different. These contains only though their own processes, and it will form a ready queue of their own. So You can consider it will be a type of matrix, okay, where each row will be its relative. We have priorities on based on process priority. RQ1, which is operating system, has more priority than interactive and background than backup. Okay. If only RQ1 is empty, okay, then if it is empty, then we will go to interactive and therefore priority of operations is maintained. Now each ready queue can use their own algorithm also. Suppose operating system use round robin, interactive use priority based scheduling. It uses its own and backup will use FCFS. We usually implement FCFS algorithm. Okay. Now this is nothing but a mix of multiple algorithms. So yeah, it is a good knowledge. We can expect this. We don't need to write much about this. So 6 multi level queue. Okay. So this is the thing of multi-level queue. Only this is important, not idea is important. Okay. These are some numericals. We are not going to solve numericals as we said. Now we will come to our main topic, the IPC and synchronization. Okay. This one's very important. So let's continue the IPC and synchronization topic, which we talked about as the main topic in the process management. So let's give the heading IPC and synchronization. So first of all, what is IPC? IPC is nothing but inter-process communication. Multiple processes should be able to talk with each other to share some resources or to share some data. Like we can see the example here. Try to understand this example first. So the process which camera recorder does is to record the current scene, and the streamer job is to stream that recording to live audience or on YouTube, Netflix, whatever, YouTube, okay. And this is done using LAN Wi-Fi to the YouTube server, okay. Now, how the data between the two process, recording and the streaming, these are two processes, okay. So how does the data between the two processes get shared? How every pixel to pixel and every data from created by camera gets transferred to streamer? We need some methods to do this, obviously, ठीक and those the data packets from this goes to RAM and RAM processes it, and then the streamer streams it, okay, makes it live. Okay, so the moment camera records 1 second of data, it has to be sent via packets to the streamer. There has to be a synchronization between process PR1 and process PR2. We can think about how storing the video in a file using process that return to the file and streamer process and reads them and sends it. Okay? Think about storing the video in a file using a process that writes to a file. Okay, so this camera recorder writes the changes the file every second, and we need to store it. So and we also need to share it. Okay, so reads them and then sends it. But since disk read and write is extremely slow, it makes more sense to store the data in the RAM. But problem is whatever is there in the dynamic memory of PR1 cannot be accessed by the dynamic memory of PR2, and vice versa. Okay, there is need of inter-process communication with the above constraint in place. Now there are certain communication strategies. You will see P1, P2, and a pipe is connected or a shared memory. Okay, and the inter-process communication. Then we will see the synchronization. There are two types of synchronization: cooperative and competing. Uh, if multiple processes are cooperating to get the task done, or if multiple processes are competing to get the hold of resources. Okay, this is part of synchronization. We will then see producer consumer problem and its challenges. Then how do we solve it using locks and semaphores and other things. Okay, so yeah, when do YouTube when we do, yeah, so this example I have told you. Then we will talk about communication strategies. Okay, yes, so uh, the first method is with pipes. Okay, we haven't wrote the notes here, but it's okay. The first method is pipes. So pipe is a file in the main memory which has some space in the main memory which both process P1 and P2 can access. It is used for one-way communication only. For two-way communication, two pipes can be set up. Pipe is a very popular concept in Unix, Android, and Linux. Okay. Pipes are used several places. So in fact, I have created a project by myself and I have used the pipes for the inter-process communication. Okay. Shared shared memory is another concept which both P1 and P2 can access simultaneously. Multiple processes can in fact access simultaneously. Okay, so we saw pipe and shared memory is another thing which is similar. Also, there is another concept called message passing. There are standard queues feature for communicating between P1 and P2. Okay. So there is another concept. Message passing is one more concept. Now, intra-process communication. We saw how inter-process communication is done. Now we'll see how intra-process communication is done. So within a process also multiple microprocesses happens, and for those microprocesses we need to communicate between each other. We usually do it by using global variables and parameters. Okay, so basically in our code, if two functions need to talk with each other or have some data shared between them, then we use global variables for those. Okay. Interprocess communication in real world can happen between two processes when processes belong to different computers and distributed systems. Okay. So there is concept called remote procedure calls in Java, RPC. Okay. So inter-process communication can happen between where processes belong to different computers also. Even if the two processes are not occurring on same computer. Example, the camera is recording on a separate computer and streaming is done on separate computer, then there is a connection between them which is established using the network, and we can do this. Now there is a concept called remote procedure calls in Java for this. Uh, I have learned about this in my cloud computing class. Okay, so now let's talk about synchronization. What is synchronization? Synchronization is basically how collectively both processes work. Okay, let's see the proper definition of few terms. Okay, so if we go here, we write synchronize. let's learn about two terms. Okay, what is parallelism, asynchronous, and synchro synchronous. Okay, so this is a simple topic, but these three difference between these three occurs very often. Okay, so we must know these things. Yeah, so it is formulating response content, a fundamental to show how modern computer but uh, manages multiple tasks efficiently. Okay, so parallelism, doing things at exact same time, asynchronous is starting now, finishing later, not blocking and coordinating the chaos. Okay, so let's read about these three things. Parallelism. Parallelism is when computer executes two or more tasks simultaneously at same instant. This is hardware level capability. It requires processor with multiple cores so that each task can have its own dedicated brain. Okay. Goal is speed, taking a massive task, splitting into smaller chunks and doing them all at once to finish faster. Rendering high definition 3D graphics. Okay, it is used in these things. Analogy, imagine a sequence and processing having one checkout lane open. Yeah. If there is one lane, then 100 people must wait in single line. Instead, we open multiple lanes and then perform it at different lanes. Okay. Now, what is asynchronous? Asynchronous will basically start now and finish at any time after. Okay. So asynchronous programming is a software design pattern where you initiate a task that takes time, but instead of stopping everything to wait for it to finish, your program immediately moves on to do other things. When the background task finally finishes, the program is notified and handles the result. Efficiency and responsiveness, preventing a system from freezing while waiting for slow operation to complete. Okay, so what is our goal? Our goal is efficiency and responsiveness, preventing the system from freezing. Okay, and our use case is downloading a large file from internet. Whenever we download, reading a database, the app remains usable while data loads in the background. Okay, so processes happens in the background. Simple, learn like this. Asynchronous, where you initiate a task at time, but instead of stopping everything to wait, immediately moves on to do other things. When the background task finally finishes, the program is notified and handles the result. Okay, it is simple, not that tough. Now, what is synchronization? We see in here synchronization, but we don't have any formal definition for synchronization. That's why I wrote the formal definition here. When we have multiple tasks happening at once, they often need to share same resources, like updating the same variable or writing to the same file. Okay. So synchronization is like the mechanism used to coordinate these tasks so they don't step on each other's toes, ensuring data isn't corrupted or action happen in correct order. Okay. So like if you have multiple tasks at once, whether parallel or asynchronous, they often need to share the same resources like updating the same variable or writing to the same file. Okay. Like the two functions are updating at the same time and we both want it. In C, it usually happens that whichever line comes first will happen first, but consider both needs writing to the same file. Then synchronization is a mechanism to coordinate these tasks so they don't step on each other toes. Like we can consider this with example. This is particular perfect example for this. if we are performing these two operations, first this, answer will be different. If first this, then this, answer will be different. Okay. So you need a perfect synchronization to perform the task properly according to your use case. Okay. So safety and order. Yeah, without synchronization, you get race condition like it is competing. Whichever will get the resource first will perform the task first. Bugs when outcome depend entirely on which task happens to finish a split second faster. Goal and order. So the goal is safety and order and preventing conflicts when multiple concurrent processes share the same memory space, and use case is managing bank balance or locking of files only. Okay, so the analogy is easy and I have given you this example. Try to remember this example for the uh, particular thing. But if you need real life example, then you can understand like this: a busy four-way intersection. The middle of intersection is a shared resource. If parallel cars try to drive at whatever speed they want, they will get crash. Traffic lights are the synchronization mechanism. They lock the intersection for one group of cars and making the others wait, ensuring everyone gets through safely and accurately. Okay, so this is good knowledge that we got from here. So we can surely now know. And then we write about this. Okay, so this is not a issue. The definition is not an issue. We wrote here every example that we could. Now synchronization, there are two types of synchronization: cooperative, like multiple processors are cooperating to get the task done. Like the cars are cooperating with each other so the task can happen. That is, everyone get home safely. But consider if it is competing. Then multiple processors are competing to get the hold of resources, like get the path, whichever cars goes first, that will cross the path and other cars will have to suffer. Okay, so this is the thing. And order of example, this is a perfect example and types difference on synchronization. Okay, it is for some temporary disasters. Now producer consumer problem challenges. Okay, so what is a producer consumer problem? We will understand the producer consumer problem by this example. This particular example explains the producer consumer problem by perfectly. Okay. So as we talked about our camera and streamer example, so the producer is the camera and consumer is streamer. Okay. That is because camera is producing the things and consumer trying to get those things. And consider the RAM that we saw there was the buffer storage. Okay, so we want a perfect synchronization between camera and consumer. Otherwise, you can imagine if we just saw 169 run to 9 wickets and suddenly it goes back to 167 to 8 wickets. Okay, uh, it will not be a good, and also that will cause errors. It is not correct actually. Okay. So the producer and consumer should have a synchronization between them. Otherwise, it will be bad. Consider if a streamer, if the camera didn't produce anything, but a streamer tries to get those things, so it will try to access an address which is not there, and it will particularly crash the computer or OS. Okay, crash the OS. So let's read the example now. In the video streaming, the camera process produces video data, records and compresses the data. Say it produces 1 second of data. The other process called the streamer, which consumes the data. The system's view, abstract view of producer consumer problem. Okay, so it has input IN as input. Yeah, okay, so producer produces in variable, not in variable, but in as a variable. Then the buffer has the buffer memory and count. The shared memory we can consider. Okay, it has a buffer array and a count. Then consumer has an out variable. Okay, and what do we assume that it is a preemptive operating system? Okay, so producer produces an open variable called in count is a variable in the shared memory, and there is an array we can think of as buffer. In variable control content tells us where to place the next content item that will be generated next. Once placed, count will be incremented. Count tells us how many items are present in the buffer currently. Okay. Using the content value of out variable, the consumer will read item from the buffer and decrement the count. Okay. Where to place the content that will be generated once placed, count will be incremented. Okay, and tells us how many items are present in the buffer. Okay, so producer will increase the count, consumer will decrease the count, in will tell where to place the next item, and out will place from where to take the item. Now Linux shared memory, this is an example. Okay, so this is nothing but some commands, and here we see the code part, how the producer and consumer code works together. Okay, so we will read this. Okay, so we are going to read this properly, and then from now we will see some ChatGPT cuttings which will explain everything. Okay, so we will mostly try to read the ChatGPT content only, and yeah, we will try to learn as much as possible. Okay, so first let's learn about this producer code. So what does it say? Producer has int item comma in variable it has acha, okay, it has item p, which is item producer, and consumer has item c, which is consumer item. Okay, and out. So while true, so that producer consumer happens for infinite time. So while producer is producing, p1 dot produce item, okay, item p, it produces item p. P2 while count equals to n. Okay, so until the buffer array is full, we can't produce and add more item. So it will keep on running until we take out item from here. And here we will, if, okay, and here also if count is 0, it means the buffer is empty, so we cannot take out any item from consumer, so it will run till we add some item. Okay. Then if we get some item that is count not equals to 0, then item C equals to buffered out when we tell which item to take out. Okay, so it will take out from that item. Out will be increased by 1 and count will be decreased by 1. Okay, and then we will consume item. Similarly here, if it is not full, then we will simply add the item at in index. Okay, then we will increase the in count and we will increase the count. Okay, it is easy, not so much. Okay, if we have, yeah, so this explains everything. If we have n elements in the buffer and the consumer has not consumed them, then there is no space in the buffer to place a new item. So the while will force to be stuck in the infinite loop. This step is busy waiting step. Okay, so it is important term, busy waiting step. This step is busy waiting step. This is also called spin lock. Okay, only when the count becomes less than n we will come out of the loop. Okay, and if there is empty space in the buffer, whatever item is that is currently produced to be placed in buffer, we increment in using mod n so that we get the next index, because index is from 0 to n minus 1. Will behave like a circular key, obviously, as I said. Count equals to 0 means there is no item in the P in the buffer. There is also busy waiting. This is also a busy waiting state. If there is an item, it will take out items. Similarly, what I explained. Okay, now tricky case. In case of producer consumer, say count equals to 5. Buffer is this. Count equals to count plus 1. Load RP. Okay, so this is some code level things. We are going to study it from these things. Okay. So race condition. Suppose count equals to 5. At the same time, producer executes count equals to count plus 1 and consumer executes count equals to count minus 1. But what is expected final answer? Expected final answer will be it will be produced and it will be consumed. So answer will remain 5. But CPU instructions are not atomic. Okay. So it is not atomic. Very important concept that it cannot be preempted. We cannot do that. First we will consume, then we will then we will insert. Okay, so it is not atomic. Atomic means if it can be preempted or not. We have seen this term before. Now, very important concept. This statement count plus 1 is not one operation internally. Machine breaks it into load, count into register, increment register, store register back. Okay, so it is not one operation. Machine will first put initial count in the register, then increment the register, then store the register back. Okay, so these three processes will happen in this just one term. Similarly, if we do this, then load, decrement, and store. Okay. Now the disaster. Count equals to 5. Producer first runs RP equals to 6. But before store, okay, before even storing. So the disaster is what? Case 1 in notes initial count equals to 5. Producers run. Okay, so RP equals to 5 and RP. But before even storing, like in the consider in the second step. Okay, we incremented, but we did not register it back. But before store, okay, before store, context switch happens. OS pauses producer, consumer runs, RC equals to 5, it decreases it. Now count equals to 4. Now memory contains 4. Now if we switch back to producer, it still has 6 in its register. So P, so the it executes count equals to 6 and we get final answer as 6. But it is wrong. It was expected to be 5. Now in case to save reverse ordering, with reverse ordering, we can get it 4 also. Okay. Now why did this happen? Let's try to understand this why it happens. It happened because both processes accessed their variables simultaneously without synchronization. Okay. So this was the thing. Now I think we should make our notes of proper understanding for proper understanding. We are going to see multiple problems, okay, like producer consider problem. So let's write something to remember. Synchronization is must. Consumer has in with count variable. Consumer has in and producer has out. Okay, so this is the whole thing. Now we can also paste the code here. It is not so difficult to understand this, but yeah, it is a good concept. In fact, most one of the most important concept. We don't need to write this story. Now the tricky case. Then you will do if the step is broken in between. Okay, so this is the whole story that happens in producer consumer problem. So now we will learn about synchronization mechanism. Okay. Okay. So now before seeing different algorithms or mechanisms, first let's talk about some terminologies. Okay. So let's see the terminologies first. Terminologies. Now, yeah, the first terminology is TF. Maybe I should write like this. Yeah, it is CS, not computer science, but critical section. Okay, so it is a piece of resource where on two or more processes fight to get. Okay, where shared resources are accessed. Portion. Okay, this is important. I don't think I should write it instead. This whole thing is important. So maybe I should just copy it. Okay. I don't know why it is so much printed. I did not name it. Really. Yeah, okay. So this is critical section. Now the second term would be okay, and also if there is no critical section, then there is no synchronization problem at all. In our camera recorder and streamer, the what RAM, the RAM that was there was a critical section. Okay, it does not need to be a piece of code. It can be a hardware too. Now race condition, the process must be racing. These are all terms. Okay. Second, race condition. The process are competing to access the shared resources. Also, if there is no race condition, there is no synchronization problem. No thing, no synchronization problem. Okay. Now for third is preemption. We obviously know preemption. Preemption can occur if scheduling algorithm is non-preemptive. Uh, then there is no problem at all. There is no issue of synchronization because one process will execute completely and then next process will execution will start. Therefore, existence of critical section, the existence of race condition and having preempted. These three are necessary conditions for synchronization problem. Okay, the synchronization problem only comes if it has a preemptive. To avoid synchronization problem, there is an idea called mutual exclusion. Now we will see the ideas. First is mutual exclusion. Yeah, then we will see the conditions for synchronization mechanism. Okay, so instead of seeing the only mutual exclusion thing, let's write here conditions for synchronization mechanism. Synchronization mechanism. Okay, so this is the thing, and the first is mutual exclusion. user, and it should be guaranteed. Like we can't work without mutual exclusion. Okay, so while one process is in critical section, other process should not go inside critical section. If one process in CS, other processes should not go inside CS. Now, what is second? Second will be progress. Yeah, this is an important term. Okay. So, what is progress? So, progress is process that are currently executing in non-CS should not block other process which want to enter the CS. Which are not in CS currently. Should not block block the processes which want to enter the CS. Okay, so this is the only thing, and these two are non-negotiable. Okay, we cannot primary condition. Then we can talk about third as bounded waiting. No process should wait forever to access the CS. Okay. It means waiting time is bounded. And fourth, no assumption about speed and CPU. This is very important for we cannot assume anything about speed and the number. by making not making we can get the general purpose operating system. Okay, secondary conditions. So the first was primary conditions. These are secondary conditions. And also these are particularly some mechanism. Okay, so this one's important. This one's really important. Okay, so these are simple, but we are going to pretty log variable strict international Peterson solution and Decker's algorithm. Hardware include TSN instruction and swap instruction, and OS based requires sleep and wake up, semaphores and monitors. We are going to study all of these synchronization mechanism. Okay, so it is going to be pretty long from now. Okay, so now let's study the first synchronization mechanism that we know. Uh, Mechanism one, which is disable interrupts. So let's write first. Mechanism one, which is disable interrupts. And what is disable interrupt? Hardware mechanism. It is hardware recipe. So it has to be supported by the CPU. CPU might have one register which says if it is zero, then your interrupts are disabled. In the entry section, we will write one line of code that says disable interrupt. It will call the OS utility and the OS changes on hardware. So enter disable interrupt and exit enable interrupt. Okay. So disable interrupt means no process can take over the critical section if P1 is taken. Okay. So basically we write the code in P1 of disabling any interrupt, and when we exit we say enable interrupt. Okay. So suppose P1 has disabled interrupt and enters in critical section. Now P2 tries to enter but can't progress any more now, as when P2 tries to disable the interrupt, since the interrupts are already disabled. It will be understood that the process P1 has is already inside the, therefore P1 gives the control relinquishes to other processes. In the exit we write in the exit section we write one line of code called enable interrupt. Once enabled interrupt happens whenever the term is for process P2. Then it will try to disable the interrupt and enter the critical section. So it is a good thing. Basically, we can paste this diagram for this. This diagram is particularly a good under gives good understanding of what disable interrupts might be. Okay, there is no busy waiting. Let's now highlight the points. Instead of highlighting, we can also write the points. Okay. So what is the first point? No waiting. Okay. It will never enter a busy waiting loop because whenever a process is in critical section, it can't be preempted. When we are solving through disable interrupt mechanism, we want to make sure that the critical section does not take too much of time, because if critical section takes too much of time, then the whole operating system is lost. Otherwise, having flexible interrupt makes this into preemptive. Okay, so it will never be a busy waiting. This has to be implemented in the kernel mode. Okay, so this will be implemented in kernel mode. Okay, what do we first we know about busy waiting? What is busy waiting? I don't think I have written here busy waiting. Like it waits. This particular part is busy waiting. Okay, so I think I should write here as busy waiting. So this is the busy waiting. We can write here busy waiting by first releasing this, then busy waiting. Okay, it does not have any busy waiting because it does not wait for it to complete. Instead, it have continue to do its work, and until it is in critical section, it cannot access. Okay, so there is no problem of busy waiting. Okay. Now suppose P1 has disabled the internet. Okay, so we have studied this. We should highlight here also that there is no busy waiting here because whenever a process is in critical section, it can't be preempted. Okay, and if it can't be preempted, then it does not have busy waiting. When we are solving through disable interrupt mechanism, we want to make sure that the critical section does not take too much of time, because if critical section takes too much time, then the whole OS is blocked. Otherwise, having disabled interrupt makes it as a non-preemptive scheduler. Okay. If it takes too much time, then it becomes like a non-preemptive scheduler. Therefore, we want it to have lesser time. Then mechanism 2 is lock variable. Okay. So now let's move to, from here we see the main mechanism things. Mechanism 2. Lock variable. After mechanism, it could have busy waiting. We can excuse it as execute it in user mode. Okay. So we can, yeah, log variable method. We should study from here. Then it is here we study about strict alternation. Yeah, we study about strict alternation here only. Okay. So lock variable. It is important because now we are going to learn about different things, and different things will be using different items. Okay. So for each item we must know its idea, because we will be when mixing few things. Okay. So lock variable, first of all, it is software based software based. Okay. Second, there are two types of things. Okay. CS free or TS occupied. Okay. Entry section before entering critical section. Okay, so it is busy waiting. Okay, because until lock is not free, we cannot do anything. So entry section, exit section. Okay, this is fine. Why it looks correct? Suppose lock equals to 0, P1 checks lock not equals to 0, condition false, so P1 does. Then why lock not equals to 0? Because lock is currently unoccupied, so it does lock equals to 0 and enter critical section. Now P2 sees lock equals to 1 and it cannot enter. But the entry section is not atomic. Okay, this is not atomic, so it has problems. Okay, so it is busy waiting. I said you just a second. Yeah, so the failure, what is the drawback of this? So we should write here the failures too. Okay, so the the entry section is not atomic. The failure case. Suppose initially lock is 0. Okay. Now P1 runs, executes this, sees this, condition false, P1 about to do this. But in between context switch happens. And how does it happen? So no mutual exclusion is there. Okay. Okay. So Suppose P1 comes, C not equal to 0. So condition false, P1 about to do this. But before that, context switching happens. P2 also runs, P2 executes this, still sees this because P1 is never okay. Okay. So mutual exclusion is failed. The primary condition is failed, okay? Because checking and setting the part. The notes mention busy waiting, okay? Also, due to this, it has busy waiting, okay? This condition is so there. So this one was important, that's why it needed this big of explanation, okay? This is our key lesson. And using hardware support, yeah, this can be tackled using hardware support. So that and set. Provenance is guaranteed in law. Okay. Also, yeah, and it is busy waiting, so it is wasted of time. Now we will study about a strict alternation. Okay. So first let's write here mechanism 3 as a strict alternation. which is strict international. It is again software mechanism designated and two process suggestion. Okay. And what is strict international? This is what a strict international is. Then we will have Peterson and TSN based synchronization. Peterson will be just mix of both. Okay. And this will now we will study TSN. Then we will study the TSN is pretty big, I guess. Okay. Yeah, so I guess there is not too much strict international. Okay. So it is a software solution code idea. Use one in term. Term equals to 0/1. 0 means P1 enters CS. P2 enters CS. Okay. This is enter strictly one after another. So here also we see it is while turn not equals to 0, it is in critical section, meaning wait until your turn either touch CS. Okay. But here also we can say it is not atomic. Yeah, it is atomic because only one process can enter at a time. So mutual exclusion is guaranteed here, but it does not guarantee progress. Okay. So mutual exclusion is guaranteed, but it does not guarantee progress. And why? We can write here mutual exclusion guaranteed, which are not there in that previous algorithm. So we can write mutual exclusion guaranteed, but no progress. So I think I should write it like that. No progress. Okay. Progress guarantee. And why it is? We saw how mutual exclusion is detected if the process is atomic or not. Okay. Now P1 is not interested in CS. P1 somewhere in LCS, maybe sleeping away. Can P2 enter? No, because P and why Okay, so we see the thing. Now we can study about Peterson solution. Okay, Peterson. This is the main thing, and it is also basically the mix of above two. It is strict internation and lock-based solution. Okay. Yeah. So let's continue the Peterson solution. So Peterson solution uses terms and flags. Okay. So instead of turn and lock variable, it uses flags. Let's write here mechanism for mechanism for Peterson solution. Okay. So uses terms and flags. One user and also it ensures progress. So mechanism doesn't take time. Yeah, let's take. But it has busy. Okay. So this is this now flag I versus I is interested in I or not. If PI is selected. Yeah, so this is what it does. Flag I if process I is interested or not. Also, this is not two process solution, but multi-process solution. So I should write it as multi process solution. Okay. So this is multi-process solution. And a turn and a flag. Okay. So currently for two processes we are seeing this as okay. No, turn will be for multi-process. Flag will just turn if it is CS is currently taken or not taken. Okay. Initially, all process flag is false. Now, if process code is present in system, then it will turn the flag I to true. That is, it is taking the uh, what the critical section. Okay. So these are the shared variables. Now, flag zero is uh, true. It means it is atomic, and also it is atomic and immediate. Now, turn equals to one. So while this is a just remember that it is atomic or non-atomic. Okay, so this is the whole code. I guess the code part is enough to learn everything. Okay, so let me paste the code here. Okay, so the coding part is enough to understand how the things are working. Okay, I just have a CD. Now I want things to be perfect. Okay, so int turn int flag this now when flag is zero flag 0 is true, it means process 0 is in the critical system now. Okay, now turn is equals to 1, which is also atomic. This process to update the turn last will wait. So here P naught will wait. The process to update the last will wait. Okay. So P naught has updated this to 1, so it will wait. So now while flag 1 equals to true and turn equals to 1, critical section, now it will go in the critical section. Now when P1 comes, it will also make it the true and it will make the turn to 0. That is, now it is turn off this to work. Here we see flag 1 is not true. Okay. So the P0 will go to critical section. After having job done in critical section, it will come out and make the flag to false. Now it will make the flag 1 to true and it will go to 0. Now as flag 0 is false, so this will not busy wait and it will directly go to critical section, and after having the job done, it will make again the flag 1 equals to false. Now we not only check the flag but we also check the turn. Okay, so as we check turn, this makes the system atomic because both conditions must be satisfied. Even if uh, this one is not atomic, it the eventually the what we can understand eventually both one. Okay, so if one condition satisfies mutual exclusion and one condition satisfies uh, what progress, we want both, so we just took end of both. Okay, so this is the best analogy we can have for the busy wait. Okay, so we can write here one satisfy progress and one satisfies what mutual exclusion. Hence taking end of both satisfies both condition. Okay, so this is the whole thing. This was the Peterson solution. Okay, it was not something so much bigger like people say Peterson solution to Peterson. No, it is very easy. So let's assume it is P naught is changing flag 0 indicating then update the value. I have explained this also. Due to this it is busy wait. Okay, turn will be 0 because turn never gets updated. It just completes one process and comes back. Okay, if we want we can read the story here, story too. Because Peterson solution is there only, now we will have TSN, the test and setting off, which is a hardware thing. Okay, so yeah, let's study the Peterson. Let's assume P naught is in the entry section. P naught is changing the value of flag 0 to 3, indicating that it wants to go to the critical section. Then P naught update value of turn to 1. The while loop is in busy waiting loop. The condition inside a while loop means if process P1 wants to go inside critical section and the turn is 1, then P1 gets stuck in the while loop. Okay, busy wait. Suppose there is preemption and control goes to P1, the P1 flag updates is to true and 10 equals to 0, then P1 while loop it also need to busy waiting as flag 0 is true and okay. Let's say P1 gets preempted and control comes back to P0. We don't need to study because we studied the code and we know what happened. Okay. Bounded waiting is also satisfies here as none of the process will get stuck waiting to go to the critical section forever. Also bounded waiting is satisfied. Okay. So we can write here bounded waiting satisfied. Okay. The secondary conditions are also satisfied from this. So yeah, it was the total thing. Now we can learn about TSL. This is a hardware, okay, thing, TSL. In TSL, just know that it makes one divisible atomic instruction. Okay, so now we can write here mechanism 5. I will only teach what is required you to know. Even though I have studied on this, you don't need to. Okay, so mechanism 5 TSL and what we saw. Just it is nothing but simple law, the simple law only. Okay. So this is TSL. We don't need to know the whole story. Also, this is multi-process mechanism because lock is also multi-process mechanism. Okay. So this is nothing but simply there. Also, the other name of unbounded waiting is Stargazer. So I guess we should write it in a block. Now, is there no option to increase the width of it? If there is not, then yes. Yeah. So the environment of one order waiting is targets. Okay. This is the thing. Priority inversion problem. Yeah, this is good. Then we will come to CMOS. Still almost 100 pages are left in this process management thing. Okay. So too much to study still. Okay, so what is priority inversion problem? So what is the priority inversion problem that occurs in TSL, Peterson? Okay, first of all, this happens due to first of all, it happens due to busy waiting. Okay, it happens due to busy waiting. Suppose priority one has priority P1 has more priority than suppose P1 has more priority than P0. Okay, P0 enters in critical section acquires now high process P1 since scheduler is P1 पे अच्छा yeah. This one's good thing. Yeah, so P0 enters critical section, it acquires now P1 arrives since it is scheduler and preemptive plus priority based. P1 immediately gets CPU, P0 gets paused. Now P1 tries to enter critical section but now already end P0. So P1 does busy waiting. Because after P1 is spinning continuously since P1 has high priority, scheduler keeps running P1. Okay, so yeah. So one thing is not releasing the lock and other is not getting the lock and so it is not able to enter the critical section. Okay. So both things are happening simultaneously and that's why like P1 has entered P1 has turned the lock to like it has locked the thing that you cannot enter critical section. But high priority comes and it takes the CPU. Now P naught is not able to get the CPU and therefore it is stuck in critical section and P1 cannot enter critical section because lock is 1. Okay, so neither the work is happening nor the lock is changing, so it has stuck. Okay. And it is like a deadlock condition. This is called priority inversion locked by a low priority process. Okay, so let's finish this part here. I don't want to make the notes so much big that you are not revising, instead you are studying. Okay, that's why I'm keeping it short and simple. Now NASA Mars Pathfinder had this issue. Okay, they solved it using priority inheritance. Lower priority in a folder temporarily boosted to higher priority. Okay, very famous operating system story. This was real life example. Now mutual exclusion without busy waiting. Can we achieve mutual exclusion without busy waiting? Yeah, we can. Now, can we achieve mutual exclusion without busy waiting? Yes. Using sleep slash wake pause. Okay. By this sleep, by this we can sleep double. In busy waiting, the P1 got CPU, but in sleep it does not get CPU, hence it is proceed safely. Okay. So this is the thing what sleep does. Now I had some doubt and I have written those doubts here. It is saying that sleep and wake up are systems calls and but using kernel mode process are high priority. So basically we are sleeping in the high priority. Kernel mode is regular level, okay? Permissions. Okay, so kernel mode is not a process. Process happens in either kernel mode or user mode. Process gets access. It is not something a process has. Process gets access of either kernel mode or user mode. Okay, so it is not that thing. Process has priority, but kernel mode user mode does not have any priority. Okay, it's about permission. Process priority. Sleep is not sleeping the kernel. Enters the kernel mode temporarily using system call. Okay, kernel updates the process to sleep. Scheduler picks another runnable process. Kernel does XOR is not sleeping. Only that process or thread is blocked. Okay, so what happens when it enters the critical mode? Kernel mode temporarily. Another runnable process. So this is the whole process. Okay. Yeah, these were some basic doubts I had. You do not need to know this. Now the lost and wake up problem. Checking condition and sleeping are not atomic. Most of the problems are due to things not being atomic. Okay. And what happens if it is not atomic? Then buffer size equals to n equals to 3. Suppose buffer initially empty, count equals to 0. Consumer starts, consumer executes this condition equals to true. Consumer is about to do, yeah, because count is 0, so it cannot take anything. So it will about to do sleep. But then the context switch happens right there. Producer runs, producer now produces these things. Now buffer is full, producer executes wake up consumer, but consumer is not sleeping at all. It was only about to sleep. Wake up signal gets lost, nobody receives it, lost, wake up problem. So we can write here. Now we will understand the lost wake up problem that occurs due to it not being atomic. Using the producer consumer problem. Okay, so this is an important thing that we need to know. So I think I should paste this image. Okay, so now producer sleeps, consumer resume. Both process both process can be in critical sections simultaneously. Yeah, it is also inconsistent. because both process can be in CS simultaneously. Okay. Assume the consumer starts executing just before it is done. Yeah, now similarly, if wake up pods can get lost. Sleeping pods can also get lost due to this both can enter the critical section. Hence, inconsistency. Okay. Now we will study the semaphores. At what page we are? We are currently at 127. Okay. Uh, yeah, this is a big topic, but we are going to study it from here. Now, most of our study will be from the ChatGPT cuts. And then we will study the reader writer problem. Then solve problems. We'll have to skip this. Then the dining philosopher problem. Yeah. So at what page dining philosopher is there? 155. Okay. So dining philosopher problem. Then we will see the semaphore based solution of dining philosopher problem. Then yeah, pair begin, pair end model. I don't think you require these things. Okay. So but still we will study this concurrent programming and okay, poke and join model. Then we will study deadlock and threads. There is too much things. Okay. Uh, so why not let's leave the semaphores for the next time. Okay. Yeah, that's all for today. So now let's continue with the semaphores. Yeah. Let's write the mechanism number 6. I guess it was. Yeah, so it was DSL. Now we have mechanism 6 semaphores. Mechanism 6 says semaphores. Okay. So semaphores are some of the most widely operating system tools and functionality in modern OS. These concepts are you will not be able to understand these concepts easily. So let's study from this. So semaphores are basically the proper solution to all the earlier problems, that is busy waiting, lost wake up, race condition, and producer consumer synchronization. Okay, we saw the lost wake up in the sleep and wake up thing. Okay, so core idea of semaphore is an integer plus waiting queue plus atomic operation. Okay, managed by OS or kernel. Why semaphores were needed? Earlier approaches failed because Jet plus sleep was not atomic, wake-ups got lost, race conditions occurred. Okay, so semaphore fixed this by making operations atomic. Semaphores make the operations atomic. So yeah, as I told you, the main problem happens due to atomicity only. So it makes operations atomic. So it is more like a concept rather than mechanism. Okay. Semaphore is integer plus waiting queue plus atomic operation. It is an integer plus waiting queue plus atomic operation. Okay, so this is basically what semaphore is. Semaphore has this structure. This is a value and a queue. So this is basically what semaphores look like. Now the two main operations of semaphore. So basically two main operations are uh, P or down or wait. It means acquire resource. P means or down means or wait means acquire resource. And V or up. See. It means release resource. Okay. So wait means acquire resource and signal means release the resource. So I understood this by keep your hands, and when you keep your hands down, you hold on to something. So it means you acquire resource, and when you keep your hands up, then you release the resource. So this is the meaning of the SEMA. This is the operation by which you can understand the down and up. Okay. Now counting semaphore can hold 0, 1, 2, 3 when multiple resources exist. Okay, so this value keeps resource count, so it can be used when multiple resources exist. Okay, 5 printers, 10 database connection. Okay, now what is this down operation? So down operation, yeah, it means I want one resource, so resource value get decreased by 1, but if it becomes equal to less than 0, then we will add the process to queue, and will sleep the process. Okay. So this is the down operation. If resource is available, it will continue the process, but if resource is not available, then simply process will be added to send to sleep. Therefore, no busy waiting. Now, what is up? Up means release of resources. So, if it is still less than or equal to zero, then we can say wake up a process. If it is less than zero, it means someone is waiting, and if someone is waiting, we can wake it up, wake the processor according to the queue, whichever comes first. This is the whole idea of semaphore. And how used to solve the lost wake up. Because taking first step sleeping here atomically inside now. So we can write it here. So as everything happens atomically, now the main code of down operation is yeah. So basically, this is the successful and unsuccess. This is what whole semaphore is. It has now two cases: the successful case and unsuccessful case. If else case in the down operation, the semaphore, that is s dot value is greater than 1, then it is a successful case, and it is unsuccessful case. Okay, this is the whole uh, thing, semaphore. Now, as it makes everything atomic, So we can basically whatever we did above, we can say, and the problem we faced can made anatomic, can make it atomic. It was initially anatomic. Okay, so this is a thing. This is the final thing. And suppose consumer requires mutex B. Okay, now what is mutex? Mutex is binary semaphore. Mutex is binary semaphore. Yeah, so this is the whole idea that you need to remember that mutex, we saw that binary semaphore is written as mutex because in my notes it is written as mutex. And also conceptually it is mutex, but binary semaphore is more general term than mutex. Mutex has its own section mutex. And semaphore is not just an integer, it is integer plus q plus atomic kernel operation. Okay, so this is the whole thing. Yeah. In producer consumer problem, we use three semaphores: empty slot, full slot, and binary semaphore. So these are the final things in the producer consumer problem using semaphore. Yeah, it is kind of important. So empty type of semaphore, the first type is empty slot, which counting semaphore, it tracks how many empty buffer cells exist. F is similarly full slots, which tracks how many filled cells exist. B is binary semaphore vertex, which protects the critical section. Reducer flow. This is the whole flow actually. Okay. First it checks is there any empty space. If E equals to 0, then we will proceed. If E equals to 0, then we will sleep. So producer consumer cannot overflow buffer. Then the P3, that is acquired mutex. Only one process may access shared buffer now. Then P4 to P5 critical section buffered in item and IN plus 1% and actually in insert item. Okay. Then we will release the mutex that we kept here. Now other process may access buffer. Now we will release full increase the full count to, meaning I added one item. Similarly, consumer flow, it will first check if item is available. If item is not available, then yeah, so This is the thing. Now higher deadlock happens. Suppose consumer acquires mutex B, then find B equals F equals to 0. Sleeps wait for item, but consumer still for mutex. Okay. Yeah, so this is reader writer problem that reads can occurs simultaneously, but writes need exclusivity. So we are at one we will do then this solving problem, then we'll solve the dining philosopher problem, the famous dining philosopher. Okay, so we'll be studying this dining philosopher problem. We can do schema for best implementation. We can log the concurrently programming construct, hope and join model. Yeah, so beyond much layer topic is here. Okay, so now let's focus on the famous reader writer problem using schema files. Okay, so what is reader writer problem? Basically, it tells that reads can happen together, but writes need exclusivity. Like can only one person can write, but reading can be done by many person. Okay, so one person can write and multiple readers can be there. So situation, multiple readers together. Yes, reader plus writer together, no, because writer needs exclusivity. And multiple writers together, no, because reading does not modify data, writing modifies data. Then why not simple mutex, that is simple binary semaphore? So what is a binary semaphore basically? It is nothing but 0 and 1. Okay, if you use one mutex for every down, read, write, up, this is only one mutex, then only one reader can read at once. Basically, you can understand this as a lock with atomic operations, and then it is wasteful. But we want multiple readers to read. Just writing things should be unique, like the not unique but exclusive. Okay. So we will use three variables: int rc equals to 0, binary semaphore mrc equals to 1, and binary semaphore rw equals to 1. Rc means readers count, MRC means mutex for protecting readers count. Okay, and RW means main database lock. Control access to said resources. If any, reader active, then writer's block. If writer active, then everyone blocked. Okay, so this is the thing. Now we see the writer code. What is the writer code? So it is very simple that it takes over everything. That is, when writer code takes down, it holds the resource, then no one else can access the resource. And when it releases the access, then everyone can access the resource. So it wants exclusive access. Similarly, what will be the reader logic? So it will take the reader's mutex, then we will increase the reader count by 1 because one reader has been arrived. And if reader count equals to 1, then we will hold down the writer. That is, there can not be any writer. Okay, no writer can arrive because reader is there. Then we will release the MRC. That is, then we will release the reader mutex at the end. So why RC equals to 1? Because whenever first reader arrives, writers are blocked. Okay, first reader locks database for all readers collectively. After that, more readers may enter, but writers are blocked. Why not? Why other readers don't down IW? Because first reader already blocked writers, so remaining readers freely enter. This is the beauty of this solution. Okay, so yeah, semaphores is a very good concept for this. And then the exit section, we decrease the count, and if it is 0, then we will release the reader's lock. Okay, and why RC equals to 0? Last reader leaving. Now writers may proceed. Okay, so this is the intuition. Close gate. First reader close gate for all writers. Middle reader just walk through. Last reader open gates again. And this is the timeline. RC must be protected. One important problem solution is reader preference solution, meaning readers may continuously enter, writer may starve forever. So this is the problem that arises, that consider if reader are coming and coming and coming and coming continuously, then the writer that has come during the first reader will keep on waiting. Okay, so this is called writer starvation, and this is very famous operating system issue. Okay, I had this doubt and I had cleared this doubt. Okay, so yeah, this was the whole reader writers problem. Now we can skip all these problems and jump directly to Dining Philosopher problem. Okay, so it was given by Dijkstra, the one who gave the Dijkstra's algorithm. Okay, so he was the same person who gave Dining Philosopher problem. So yeah, Dining Philosopher problem is not so that tough of a topic. Okay, concurrent program, we can skip this concurrent programming. Okay, in fact, we will skip this concurrent programming. We don't need to know all these in particular. Then this pair begin, pair end. This is good for the gate representation, but not for the placement point of view. Yeah, but we need to know the concurrency. So we will know the concept of concurrency, and then we will know the concept of walk and join model. Then this will come at what page we are currently 180. So and this will continue till 213. Okay, so it is quite long journey still. This is the dynamic philosophers problem. So we are currently at page number 154. We'll continue from that. Consider our half of the chapter is already more than half of the chapter is already completed. Okay, so now we will complete this by tomorrow. Okay, so now let's study the dynamic philosophers problem. As I have mentioned, it was given by Dijkstra. Also, the concept of semaphores was introduced by Dijkstra. Okay, he wanted to understand the power of semaphore and how they are to be used. So now dynamic philosopher is a theoretical problem, but very interesting problem. Okay, it does not map exactly to real world problem, but it tells about the complexity that is involved in designing proper or well synchronized process, which do not have deadlocks using constructs like semaphores. Okay. So semaphore, it is just an application of semaphore. It does not map to any real world problem, but yeah, it can happen due to deadlock. We will see how deadlock appears in this problem. So basically, uh, if I will have to show you a animation of dynamic philosopher, I there must be some animation regarding this on YouTube. Okay, and dynamic philosopher is quite a common problem. Philosopher's problem animation. I guess, yeah, I have seen one of the videos. Okay, so
This is the example of dining philosophers sit at a round.
what we observe that few people are standing in a round table. Okay, not standing but sitting in a round table. They have some food in front of them, and between every two people there is one fork present. Okay, and to eat the food, a person needs both of the fork from its both sides. Now, if every person starts taking fork from left to right or right to left in in an order, then what happens is everyone gets one fork and no one is able to have their food, and it is a deadlock like situation. Like no one can even eat their food, and no one can leave the fork. Okay, so this is a deadlock. We see here an animation.
Chopsticks are placed between the rice. So chopstick, however, will pick up it for the second chop. So will have one chopstick in their hand and will be waiting for the second chopstick
At once.
because
So we see it is a counterclockwise type situation from, you can say, right to left. Okay, or whatever, counterclockwise, not right to left or left to right. Okay, it is a counterclockwise thing. Everyone have one fork and they are not able to eat their food. This is a deadlock situation. That's all. Now let's see how semaphores help us to solve this type of problem. This is just the explanation of the dining philosopher problem. They need both folk to eat the food. We can think of folks as resources. There are five philosophers and five folk, therefore every philosopher cannot eat. No, there are five plates with food on the table. Okay. Yeah, so I have explained you. Now the solution one would be the most naive solution. The code is given here. We will see the algorithm here. And the second method will be a non-semaphore based solution. And third non-semaphore based solution would be this. And finally, this is semaphore based solution. The explanation for this is given here. Okay. This whole is the same problem. So first of all, let's study the solution one. First of all, let's write about what we are studying next. So we are seeing the next thing is dining philosophers problem. So this is part of semaphores only. So this is mechanism. Dining philosopher problem. Let's draw the diagram like this. I guess there must be a say person. Yeah. And persons sitting near this. Okay. So I suppose six people are there. Okay. So yeah. And food is kept in front of them like this. And a fork is present between them. Fork can be considered as a resource as we have talked about it. Okay. Now, if anyone wants to eat, he needs both of the forks. So the solution to it. Solution one, let's talk about. This is the most naive solution. Suppose I equals to 0. I starts to think. I gets hungry and picks up the left fork. Then I picks up the right fork. Then I eats. Once done with eating, put left fork down, then put right fork down. Simply. That if anyone wants to eat, he will pick both of the fork. Now let's check if the solution is good. In the world of multiple philosophers, say philosopher 0 pick up left fork after he thinks and when he gets hungry, let's say P naught gets preempted now and control goes to P1. P1 starts thinking and when hungry, P1 takes the left fork and gets preempted and control goes to P2. Okay. In this similar fashion, P3, P4 also takes the left fork and control comes back to P0. P0 is waiting for P1 to give the right fork. P1 is waiting for P2 to give the right, and similarly for the rest. And P4 is cyclically, yeah, waiting for P0 to give up P4's right fork. All of the process are in deadlock. So it still, even after this solution that one takes fork and takes both fork and eats. Even after this, there can be deadlock situation because if preemption happens in between, like he picks up the one fork and while he was picking the second fork, preemption happens and P1 picks up the second fork. So that's the situation. And that's why this solution is not so good because deadlock can still happen due to preemption. So first let's write the algorithm. P naught picks both forks, eats, leaves both one by one. That is first left, then right. Okay. So yeah, this is the thing. Then he eats, then he leaves both the forks. One by one again. Okay. Now solution. Now the problem with this. Suppose P naught picks left 4. Then Y going to pick preemption occurs. Okay, preemption occurs. And P1 picks that. Then Y again going to pick a 4 in the right of P1. Preemption occurs for P1 and because similarly this can happen for all and no process eventually get the no process. Okay, and deadlock situation occurs. Okay, so this is the whole thing. This is why this is bad. Therefore, we would like to think of solution without using synopsis. Then once you have for best solution, pick right fork, then pick left fork. Again, this is not a valid solution. Say 0 to n minus 2 philosopher picks left, then they right fork. While n minus 1 on the last philosopher picks the right fork, then left fork. In this scheme, when philosopher 3's turn comes again, he picks the right fork and finishes eating and places both the fork back. Then P2 can pick the right fork and complete his meal and place both of the fork on the table. This way we can avoid the cyclic wait. Okay. So solution 2 would be this. Solution 2. What would solution 2 be? 0 to n minus 2 philosopher will pick left, then right. N minus 1 philosopher will pick right, then left. Okay. So this is one of the solution. Now the third would be let odd number philosopher pick left fork then right fork, and even number philosopher will pick right fork and left fork. So solution 3 would be odd number philosophers would pick left then right, and even number would be philosophers would pick right then left. Okay. So yeah, this is the again one more solution. Now the semaphores based solution. Also here no deadlock, and these all are semaphore based solution, non-semaphore. Okay, these are non-semaphore based solution. Now we will have solution 4 which will be semaphore based solution. So first let's see how semaphore based solution works. Okay, earlier solution were ordering track, asymmetry track, but this one is actual synchronization style solution using semaphores. Okay, so now let's understand this slowly. Yeah, so the main idea is instead of philosophers directly grabbing the fork, like left fork and right fork, we need the OS control who is allowed to, and that is the key. Okay, so instead of every philosopher taking the fork, we just let who is allowed to eat. So we will maintain three states: thinking, hungry, and eating, as we have talked about. Uh, I guess I have not explained you how what are the states we consider in a philosopher. Okay, so philosopher can either think or can eat. Okay, he can't do any. He can't do both of them. So if he is thinking, that is, he is not currently eating, then we will mark that state with number 0. If he is hungry, that is, he want to eat, but there is no fork available, then we will mark it as 1. And if he is currently eating, then it will be marked as 2. Eating means both of the forks around him is occupied. So each philosopher has a state I. Now, example, philosopher P0 is thinking, philosopher P1 is hungry, but philosopher 2 is eating. Okay. So semaphores used is first is binary semaphore is used, mutex semaphore. This protects the shared variable state checks update, meaning one philosopher at a time can modify state. Okay. Now a personal semaphore is also there. This one's global semaphore and this one's personal semaphore. So each philosopher has its own semaphore, and this is extremely important because think SI has permission for philosopher I to read. Okay. Initially all blocked, or we can say everyone is thinking. So everyone has got the state 0. Okay. Now left eye and right eye, these are just computers. For n equals to 10, left eye is I minus 1 plus n%, and this is just mathematical expression for computing the left in a circular manner. Okay. For example, if I equals to 0, then left is 4 and right is 1. Okay. For a circular table, this expression is used. Now philosophers loop. While think. Okay, so while true, it is thinking as long as it wants. Then it takes fork I. It takes the ith fork. Then eat. Then put fork or return the fork. Okay. So think, request fork, eat, release fork. Now this take fork function is like this. So it has got the down. Now state I will be changed to hungry. That is, he is requesting to take the fork. So he is interested. So he is interested in ith fork. So ith fork state is changed to hungry. Now we will test if I is present or not, currently free or not. And if it is free, then we will give it to him. Then he will eat. Then we will uh, release the fork. Okay. So state I is hungry, test I, release I, and then I guess SI will get. Okay. So down lock mutex, nobody else can modify state. State I hungry, philosopher says I want to eat. Now test I. What does test I? This checks if left not eating, right not eating. Okay. If no one is eating. Okay, so okay. I am thinking about I is folk. No, I is not folk. I is philosopher. Okay, so if I is philosopher, he wants to eat, he will the take folk will mark his state as hungry. Now it will test, and what test does, it checks if left not eating, right not eating, because if any one of both is eating, then there is no folk available for him. Okay, so if left not eating, right not eating, then philosopher can eat. So test I will be state I equals to hungry, state left I not equals to eating, state I right I not equals to eating, then state I will be eating, that is ith will start eating, and will release the SI. Is there SI? Where is SI? SI was mentioned anywhere? I don't think so. Yeah, here. Personal semaphore. Okay. So SI was a personal semaphore. So SI will be marked as a SI will be released. Okay. So it means if both folks are effectively free, we allow philosopher I to eat. Notice we are not literally storing folks. Yeah, that was that mistake I was making while explaining. Okay. So we are not storing the fork. We are using neighbor states, and this is a brilliant abstraction. Okay. Yeah. I got confused. Okay. Now why up SI? Remember down SI comes later. So philosopher can eat. Test does up SI. Down SI succeeds immediately. Otherwise down SI blocks philosopher. This is basically sleep until all folks are available. Okay, so okay. So what does down does? What does down do? It uh, makes it sleep. It makes the ith philosopher sleep until both folks are available, and whenever both folks are available, it wakes it up and it the philosopher takes both the fork. Okay. Now important insight. This solution never allows everyone grab one fork. Okay. Because until and unless uh, one completes its meal, the people in the neighbor of them, in the neighbor of him, cannot eat. Okay. So yeah, one must complete its food, then the neighbor can proceed. That's why no one gets one fork. Here, a philosopher either gets both logically or gets none. That is the difference. And what does put fork does is simply reduces it to thinking. That is, he is not currently eating and he does not even want to eat. Now, test is done for the left eye and right eye that if it wants to eat and if it does not want to eat, and then it is get released, meaning I finished eating. Checks whether neighbor were waiting. Okay, so it checks if neighbor were waiting, and if yes, then wake them up. This is very naive solution and easy to understand. The thing about uh, operating system solutions is that it is easy to understand. Okay, so this solution works because fork acquisition becomes atomic logically. Take left, wait, take right, partial resource holding calls. Now, permission granted if only both are available. Okay. And now why mutex M is needed? Suppose two philosophers simultaneously do this. Without mutex, race condition happens. Both may think folks are free. Mutex realizes they interpret. Okay. So what does this M do? It serializes the state update. So I guess I should write here. Serializes state update, otherwise race condition could happen. Serializes state updates. Otherwise, race condition may happen. This is not really controlling folks directly, it is controlling permission to state, semaphore, neighbor checks, and that is the elegance. Final mental model. Think of the waiter system. Instead of philosophers grabbing for themselves, philosopher asks waiter, "Can I eat?" Waiter checks neighbors. If safe, yes, else wait. Yeah, so this is the thing. I think the file got too heavy. And how does this happens? So this is the whole code. This is the same thing that we explained just right now. This was pretty awesome. From the concept to the solution, everything was awesome about this. Okay. And that is the beauty of semaphore. Now concurrent programming paired begin and paired end. If we can execute two or more statements parallelly, imagine. Yeah, so this one's important. I guess I have told you this one's not important, but uh, this is a concept used in parallel programming, and parallel programming is one of the most important part of operating system. Okay. This one's not important. The programming constructs. Okay, concept is required, but not the programming construct that how we are going to write the graph and all. Now, as I have written here, just know the idea and example, not code. Okay. Yeah, so we are pretty soon on the close up of this topic. Let's move to the next topic, which is concurrent programming. Okay, so this is the next topic, concurrent programming. This is not so hard. So now, as we have seen, this is concurrent programming is much required. Okay. So it is used in multi-core CPU, GPU execution, database transactions. Yeah, in DBMS also you will study about the concurrent program. So the whole game is can two instructions execute simultaneously without changing the final answer. First example, A equals to B plus C, D equals to E plus E into F, K equals to A plus D, and L equals to K into F. Now observe S1. This process produces A, S2 produces D, S3 needs A and D. So S3 depends on S1 and S3 depends on S2. Okay. So we want answer of S1 and S2 to proceed. Therefore, these can run together, S1 and S2, because they are independent. But S1 and S3 cannot. Why? Because S3 needs output of S1. Now, in precedence graph, it is a type of graph. That diagram, there is a diagram. Yeah, this is a precedence graph, and this is also called the dependency graph because it shows you S1, S2 dependent on S1, and S3 dependent on S1, and S4 depends on S2 and S3. Okay. Example S1, S3. That is S3 must happen after S1 and S2. And S4 must happen after S3. Okay. Now, very important idea. Compiler or OS tries to find which instructions are independent. Independent ones can execute concurrently on different CPUs in parallel pipeline. Okay. Uh, this improves speed. Okay, so independent ones can exist concurrently or different CPU in different pipelines. This improves speed. Okay. Now the mathematical model is there. We see. Okay. Read set and write set. This is called mathematical model. Example: A equals to B plus C. So it first reads B and C and then writes in A. So read set consists of B and C and write set consists of A because B and C are read and write is done on A. Similarly this. So here if we think all three are write set. Okay. So all three are read also or three are write also. Here A is not read, A is only written. Okay. So read set equals to A plus B plus C and write set equals to A. Not A plus B plus C, but A, B, C, and write set is also A, B, C. Okay. Now, Bernstein conditions. This is the real theorem. It tells when two statements can execute safely concurrently. Okay. So suppose Si and Sj, then concurrency is allowed only if. Okay, suppose Si and Sj, then concurrency allowed if Si and read Si and WSJ is empty. That is, they must not have any common. That is, so we have been given two statements, like suppose A equals to B plus C and D equals to E plus F. Then two statements can execute concurrently if read of first statement, that is B comma C, and write of second, that is D. Basically independent. Si should not read something that Sj writes. Okay. Independence must be there between both. Similarly, opposite of this case, that Sj should not read something that Si writes. Okay. Or if both writes, then both should be empty. These all three conditions should satisfy. Then we can safely execute two concurrent statements. Okay. But this can happen safely. Like there is read of Si and read of Sj. Intersection of this not necessarily be empty. Okay. Both statements may read same variable and this is completely safe. Multiple readers are okay, multiple writers are not. We have seen the readers writers problem before. Okay. There also the condition was the same. So real intuition, concurrency danger comes from shared mutable state. If no shared writes safe. And what is this called? This is called Bernstein condition. Okay. So this was Bernstein condition. Let's write what are the topics we saw in this. So first of all, the first topic we see here is the dependency graph. Also called precedence graph. And then we read about read set and write set. Then third we studied about Bernstein And what is this? And similarly for this D and F. These all should satisfy. Yeah, so I was talking about all three should satisfy. Then uh, concurrency is possible. C. Okay. So this was concurrent programming, complete concurrent programming. Okay. And this term is good. So I guess I should write this term. Okay. So yeah, this is concurrent programming constructs for concurrent programming like pad begin and pad end. You don't need to study it that much. Okay. Now fork and join model. Let's write here. I guess that was heading of concurrency. And I guess I would like to make this that, yeah. Okay, so let's study this now. So what is this fork and join model of concurrency? We modern systems actually use this idea with like threads, OpenMP, Java, fork join. Okay, before everything, let's study the fork idea. Fork means create a parallel task. Join means wait for parallel task to finish. Okay, so if you have ever used the GitHub, you know that when we do fork, we parallelly add more features to the existing GitHub repo. Okay, so the same thing is here that fork means creating a parallel task and join means wait for the parallel task to finish. Now, in this graph, we see S1 to be executed first, then split into two parallel branches, S2 and S3 both run concurrently. After both finish, execute S1. So this is classic fork join code model. Now, this is the thing, join count and code. We don't need this. Okay. So we just need code idea, which is fork means this, join means wait for parallel task to finish. We can just learn S1. This code is very. This becomes very hard to understand better. Okay, but we must know that there exists something called fork and join model. Okay, of concurrency, which states uh, this. Okay, so concurrent programming is also completed, I guess. Now deadlocks and threads. Deadlock handling prevention. Okay. Now deadlock with then deadlock prevention. Okay, so deadlock prevention has certain algorithms attached with it. Banker's algorithm is one of them. After this, I guess, yeah, deadlock detection and recovery. Then multi-threading and multitasking. Single threaded versus multi-threaded, then multi-threading versus multitasking, then hybrid threading, and yes, memory management then comes. So I guess this is completed. The process management will be completed. Memory management is like smaller than this. If you will see the page 213, and it is max to max 70 to 80 pages. So after completing this deadlock, we will study this memory management tomorrow, and yes, our complete um, this thing operating system will be completed. Okay. So yeah, we are pretty close now. This part is easy. This is not, to be honest, tough to understand. But yeah, it also requires some focus to be made. So we simply write here deadlocks and threads. Deadlocks and threads. Okay. Okay. So deadlock is a condition where two or more process wait forever for an event to happen which will never happen. Okay. You can see here resource A and resource B are present. Resource A is associated or allocated to PI now, and resource B is allocated to PJ. Okay. Now this process I request about to RB and process J request to RA. But to complete the process, PI needs both the resources, and this is held by this. This is held by this, and this is held by this. So neither the process can complete nor it can leave the resource because no process wants to leave the resource it got. Okay, and no process can complete because the resource it has is partial. Okay, so this is a deadlock like condition, and this is just add-on notation that if it is from resource to process, it means resource is head, and process to resource, it means it is the requested. Okay. Now, similarly, this is the resource allocation graph, RAG. RAG to weight graph. Okay, so we convert the RAG resource allocation graph to the weight graph. This is simple because if you will see that, let's see this. So there is a resource R2 present. R2 is allocated to both P1 and P2. Now P1 is requesting for R1, but R1 is allocated to P2. So until and unless P2 completes, P1 cannot complete. Okay. So first P2 will complete, then P1 will complete. This is what it is saying that P1 is waiting for P2. Okay. And P2 cannot complete because the resource P2 is asking is dependent on P3, is allocated to P3. Okay. And also R4 is another resource which is allocated to P3. But since R3 is allocated to P3 and P2 is requesting for R3, it means P2 will wait for P3 to complete. And now the P3 is requesting to get R2, but R2 is allocated to both P1 and P2. So P3 is waiting for the resource that is allocated to P1 and P2. So P3 is waiting for P1, P3 is waiting for P2. So this is a deadlock-like condition, and this graph is called weight graph, and this graph is called resource allocation graph RAG. Okay, so this is the whole thing. Now the conditions for deadlock. There are four conditions for deadlock. The four conditions are mutual exclusion. If mutual exclusion is there, that that is there a critical section. Okay, so let's understand this better from this. Okay, resource allocation. We understood this resource allocation graph and the weight graph, circular weight. Now the necessary condition. Yeah. So this is a necessary condition for deadlock. There are these are very important because all four must happen together. If any one of the condition is not satisfied, then deadlock is break. Okay. So for deadlock to happen, all four resources must, all four things must happen together. Mutual exclusion. Only one process can use resource at a time. Example, printer, mutex, log, semaphore. Okay. If everybody could share resource freely, then there is no deadlock. Okay. It means only one process can use resource at a time. Hold and wait. Already hold some resource while waiting for more. Okay. This is the thing like mutual exclusion. Only one process can use resource at a time. If everybody could share resource freely, then there is no deadlock. Like if R2 can share from here, we can see if this can share freely to this, but here we see it is specifically allocated to P3 and it cannot share its resource to P2. So there is a mutual exclusion here. And this is the thing, mutual exclusion. Now hold and wait. Versus process already holds some resource while waiting for more. So P1 holds R1, but it waits for R2. So hold and wait process already holds some resource while waiting for more. Now no preemption. That is, you cannot forcibly take resource away. If preemption is there, then it is very easy to prevent deadlock because you can just take the resource from one process and let the other process complete it itself. Then we will allocate that resource to the original process. Okay. Now circular wait processes form a cycle. This is actual deadlock loop. So the very important theory, our notes mention cycle always not always equals to deadlock. Okay. It is not necessary that if there is cycle then there is deadlock. But if there is deadlock, there got to be a cycle. So yeah, it is easy to understand. Okay. But there are cases. Suppose each resource has one copy. Then cycle is deadlock. But if multiple instance is there of resource, then cycle may exist, but deadlock may not exist. Now there are four approaches to handle the deadlock. First is prevention, which means break one of the four conditions. Second is avoidance, that if we avoid, if we allocate resource such a way that system stays safe, then it is good. Prevention, if we can break one of the condition, then there is no deadlock. Third is detection and recovery, that is allow deadlock. Later detect cycle, kill the process. Okay, so kill processes and roll back. So this is detection and recovery. And fourth is ignore. This is funny but real because uh, preventing or avoiding deadlock is costly process. So we mostly try to ignore it. This is called ostrich algorithm, means pretend deadlocks rarely happen because deadlock handling can be expensive. Okay. One core to remember. One core idea to remember, deadlock is fundamentally dependency cycle plus non-shareable resources. Everything in these nodes revolve around that cycle. Okay. So this is just the deadlock thing. We'll study all of these things. But first, let's write what are the things we are studying. So first we are studying what? Uh, we studied weight graph, but we also studied resource allocation graph. Resource allocation graph. Then what we studied? We studied the weight graph. Then what we studied third? Conversion of resource allocation graph, weight graph. Okay. Then what we studied? Necessary conditions for deadlock. And what are the necessary conditions? First is, let's change the page so we can try to remember. Okay, mutual exclusion. The first is mutual exclusion, and what does it mean? One resource is allocated to one process at a time. One resource is allocated to one process at a time. Now, what's the second condition? Second will be hold and wait. What does this mean? One process is holding a resource but waits for another resource to complete. Okay, so this is the idea. Now, third will be fourth is cycle. I know what is third. Okay, so this is mutual exclusion is first, hold and wait is second. What can be the third? Fourth is cycle, but what can be the third? Okay, if you're forgetting, we can take a look at this for comprehension. Yeah, that's why we need to revise without seeing the answers so that we can fit things into mind. No preemption, no example is, no explanation is needed for that. And fourth is cycle. But remember, deadlock equals to cycle. But cycle does not mean deadlock. Okay. So these are the four conditions for deadlocks and threads. Now let's study the methods to cure. What word has been used? Methods to handle deadlock. So first will be prevention. Second will be avoidance. Third will be prevention, avoidance, wait and kill, something like that. Yeah, detection and recovery. So detection and recovery. And fourth would be ignore. So this is ostrich algorithm. And this would be banker's algorithm. And banker's name is not on scientist but really banker, like the bank. Okay. So yeah, these are the four methods to handle deadlock. We will study on these in detail. Okay. Mostly we'll read the ChatGPT cuttings now only. Yeah, so uh, for the deadlock prevention, all four conditions must go held true. Okay. We saw the four methods, that is prevention, avoidance, detection, and ignore. Okay. So the prevention method works on if we break any one condition, deadlock becomes impossible. Okay. And how can we break one condition? Mutual exclusion. How can we break mutual exclusion? This is not dissatisfiable. Means you cannot remove mutual exclusion. It is a required condition also. Okay. So mutual exclusion is not be removed. Now prevent, hold, and wait. This is the biggest section of hold and wait means process hold some resources while waiting for more. To prevent it, OS use two resources. Request everything initially instead of request R1 and then later request R2 do R1 and R2 together like atomically. Okay. It is highly inefficient because process may hold unused resource for long time. Yeah. If we request everything initially, then what if few resources we require later, but those resources are captured while we try to complete it. Okay, so it is inefficient. Here example of given of printer structure. Release everything before new request. Before you make a new request, release whatever you have till now. So process never will frustrate simultaneously. Plotting discover starvation. Some inductive process may never get all resources back. Okay, because if releases the resources, what if it needs the resources back, then it can never get back because that resource will be like trapped in some other process. Now, no preemption. So prevent no preemption. That is, we should be able to preempt. Original condition resource cannot be taken forcefully away to prevent deadlock, allow preemption. Okay. So now why this prevent deadlock? Because deadlock cycle requires P1 waiting for it. If everybody knows your plan, if there anything we have missed, yeah. So we have only reached fairy tale. Prevent. Now the fourth condition is also there. Before that, let's read the type of preemption that we can perform. First is code script preemption. OS forcibly removes resource like fake CPU or from process. This is possible for CPU and memory pages, but this is hard for printer middleware printing because we cannot take the printer while it is printing. So it is hard for that. Second would be graceful self-preemption. So process voluntarily releases resources. Example, could not get next lock, release previous lock and retry. Okay. So yeah, these are two types of preemption. Take away CPU from process or voluntarily releases resources. So this prevent the deadlock from happening. But again, if starvation is there, okay, one process may repeatedly lose resources. Now, fourth is prevent circular wait. This is very important. So my notes assign a global ordering IDs to every resource. Okay, give every resource in order. Like first give for R1, R3, R8. Like according to the ascending order of global ordering IDs. Okay. But this is not allowed because order decreases. So we want order to be straightforward. Why this happens? Deadlock cycle requires P1 wait for smaller, larger mix, P2 waits backward, P3 waits backward. If everybody moves only forward in ordering, then cycle becomes impossible because cycle requires coming back. Okay? Right here also if you see um, from the diagram, yes. So we see here it comes back. Okay. If it does not come back, then we can set P3 completes, then P2 completes, then P1 completes, correctly. So no deadlock. Okay. So we want to prevent the uh, requesting for resource backwards. Okay. Now the example given is this. P1 holds 1, 2, 3, 4, 1, 2, 3 and waits for it. Yeah, this is fine because it is waiting for the resource in larger. But if it holds 8 and wait for 3, it is not allowed because uh, it breaks order. Okay. So yeah, this was the total thing. Prevention methods. So we can write in this break any one of the four. One, no, four condition. Now if we uh, copy here the conditions, so this cannot be broke. We can erase this one. Cannot break this condition. Okay. Then for the second one, hold and wait, we can prevent this either A request everything initially or the release everything before main request. Okay, so yeah, these are the two conditions. These are the two methods for board with for no preemption also, forceful preemption and graceful preemption. Okay, forceful preemption, graceful self preemption. Now cycle. Hmm, ascending order of global process ID, global ordering ID. Yeah, so this is how we can uh, do the prevention method. Now let's see the second method, which is Banker's algorithm. Okay, so Banker's algorithm is the second method. Second will be avoidance. And how does this work? Deadlock is allowed to potentially happen, but OS carefully allocates resource so system never enters a dangerous state. OS carefully allocates resource so system never enters in it's fine. Isolistic base only. And this is the main idea. You can if after giving this resource, can all process still finish somehow? If yes, then grant the access to the resource or don't allow lock the process. Okay. Now it is not so tough to understand. Okay, so let's try to understand before writing anything. Important term, suppose m processes are any m resources type. So we first create a m m well, matrix. Okay, maximum number of resources Rj that process Pi may ever make. Okay, example, um, max P1 printed 5 equals to P1 may need at most 5 printer. Okay. Now allocation, how much resources allocated, how much instance of resource RJ is allocated. Now need NM means max minus allocation, how much need is still there after allocating, and available M resources currently free in system. Okay. So safe state versus safe state. Safe state, if there exists some order in which all processes can finish, this is called safe sequence P1, P3, P1. Okay, P1 finishes first, releases resources, then P3 can finish. Everybody eventually completes. This is a safe state. Unsafe state means no guaranteed completion sequence exists. Unsafe equals to deadlock. Okay, unsafe will lead to deadlock because uh, it will not reach the safe state. And how? So there does not exist any order in which all processes can finish. And if all processes cannot finish, then deadlock will surely happen and that will unsafe will result to deadlock immediately. But unsafe can potentially lead to deadlock. Okay, yeah, that's what I explained. Now, what is the safety algorithm? Work, this is very easy by the way. Initialize work equals to m level, finish equals to finish I equals to for that is the process is not finished yet, and work is equals to m level. Okay, so m level array we have seen. Okay, no, we have seen allocation array. Okay, so work equals to m level is something. Okay, find some process pi where need I is less than work, meaning current available resources are enough to finish pi. Okay, return pi completes. So work equals to work plus allocation I, because after completion pi delivers all the resources. Mark finish I equals to true. Repeat until all processes finish or no further process can finish. If all finish I become true, then it is safe, else it is unsafe. What is resource request algorithm? This is actual runtime part. Suppose process request resources. So OS checks if request is less than need. Otherwise, process is beyond declared maximum. Okay, so it is illegal. That is, if it requests more than what it needs. Now, it also checks if request is less than available. That is, if we don't have that number of instances of that resource, then resource is available, then process will simply wait. And check 3 is pretend allocation is granted. So available minus request and allocation plus request and need minus request. Now check 4 run safety algorithm. So safety algorithm we see here. Okay. So if state remains safe, then grant request, else roll back and log the process. That is, that process cannot be performed. Now there are some limitations that is important for exams or can be asked in interviews also, that what are the limitations? So first is must know maximum need in advance. That is, we must know how much instances of the resource is required by the process. And number of process that changes dynamically. Process start, terminate, fork continuously. So banker assumes static environment rather than dynamic environment. Suppose if process requires currently 5 resource, but later due to some changes it requires 10 resource. But as we have already filled our matrix with 5 and calculated based on it, so we will give our result as yes, the process can run, but in reality it needs 10 resources, so process cannot proceed further. Okay, these are the two limitations. That is, we must know maximum need in advance and number of processes change dynamically. Okay, so banker's algorithm, not tough. Banker's algorithm is very easy. Okay, so read from notes. These are not notes actually. These are just for the division. Okay, I can't just stick all of these cuttings. So yeah, this is Banker's algorithm, and after this, our most of the parts have been completed of prevention and avoidance. Now detection and recovery. So detection and recovery is the only thing. After this, what? Ignore. Simply ignore. Okay. So it is nothing. Yeah. So deadlock detection and recovery. So earlier we have studied the prevention and avoidance, the banker's algorithm, and this. Now let's allow what is detection and recovery. So we allow the deadlock to happen, then detect it, then recover from it. Okay. So the third would be detection and recovery. Detection and recovery. Okay. So what it says, allow deadlock to happen, then recover. Detect it, then recover from it. Okay. So two cases exist. One, single instance resource. Example, one printer, one tape drive. Only one copy exists. Okay. In this case, we use the wait for graph. Okay. So if only one instance of every resource is available, then we use the wait graph for this. Instead of showing resource, we directly show the processes. Means PJ is waiting for this resource, and this is waiting for this resource. And if there is any cycle in this graph, then it is necessary and sufficient condition for deadlock. Okay. When when should OS run detection? What is this? Okay, yeah. Now case 2 is multiple instance resources. Example, many printer, many semaphore, many buffer. Now cycles are not enough. So OS uses modified safety algorithm, very similar to Bankert safety algorithm, which some processes can never finish. Then deadlock is detected. Now, when should OS run detection? Low CPU utilization, many block processes, meaning system behaving suspiciously. Then OS may run deadlock detection. Okay. CPU utilization is low, that is not utilizing at the level it is made, and many processes are blocked. Then it is suspicious that there must be a deadlock. There may be a deadlock, not much. Okay. Now recovery mechanism. So suppose deadlock is detected. Now what? There are two major recovery mechanisms. First, process termination. Kill processor. Two. Kill all deadlock processes. Kill one process at a time. Okay. This is the first one is fastest but terrible. Lose all progress and restart everything. But second one is check if after killing deadlock is present or not, or continue until cycle breaks. Okay. So this is easy. And second would be the to resource preemption. Okay, instead of killing processes, forcefully take the resource away. This is same as forceful preemption we saw in the avoidance method. Okay, avoidance or what it was? No, prevention. Okay, it is the same as we saw in prevention. So this also breaks deadlock. Important problem is starvation. Some unlucky process may repeatedly lose resource. Yeah, this can happen. Repeatedly roll back and repeatedly get killed. So now, what is rollback? Process periodically save checkpoints. Okay, A, B, C, D. Suppose deadlock occurs at D. OS may roll back process to checkpoint C. Resource acquired after C are released. This may break deadlock. Okay. So if deadlock happens at D, then resource acquired after C are released. So this can break the deadlock. Okay. But yeah, this is the problem starvation. Repeatedly losing resources, repeatedly roll back, and repeatedly get killed while others continue. This is starvation and it occurs for one process. Okay, one or two process, whatever. Now this is single threaded versus multi-threaded. Is there anything after that? No. So this is the last topic that we are going to study today. Hmm. What is multi-threading? Now we will write with multi-threading and single threading. Multi-thread and single thread. Okay. So this is our new topic. Single threaded process, only one execution flow. Memory contains code, data, files, registers, stack, and only one stack plus one program counter. So only one task executes at time. Okay, so in single thread, threads are just microprocess, you can say. Okay, so if there is single thread, then only one task executes at a time for that process. Okay, normal C program. Now multi-threaded process. A process can contain multiple threads. All threads share code, data, heap files, but each thread has its own registers, stack, program counter. Okay, so T1, T2, T3. These are multiple threads. Threads are lightweight processes. As I said, these are microprocessors because creating switching them is cheaper than full processors. Now, the notes mention better CPU utilization, CPU stays busy, easier shared data access, same address space, faster context switching, smaller state, responsiveness, GUI won't freeze, and parallelism, multiple CPUs execute threads. Okay, so multi-threading is this. We can write about single thread and multi-thread here, but instead I'm just going to stick these notes only. Okay, these are good written notes. Not good, but yeah, not written. Actually, these are good, but not written by me. I have given a specific prompt to make it more understandable. Now, why multi-threading? Because better CPU utilization, CPUs stay busy, easier data shared access, faster context switching, responsiveness, parallelism. Okay, there are many benefits of multi-threading. Now, what is multitasking versus multi-threading? Multitasking, multiple processes. Multi-threading, multiple threads inside the same process. Threads shared memory, communication becomes easy. Okay. Now, what is the difference between process and thread? Memory separate shared. Creation cost high, low. Context switching expensive, cheap. Communication IPC needed, direct memory access. So yeah, this one is also good. Okay, and now this difference. This is very important in context of in terms operating system. Okay. So now our second is client server architecture. So web server and thread pool. Instead of creating thread per request, pre-create worker thread. This is one thread tool used in everywhere. Um, hybrid threading. Is there anything that is required? Yeah, so this is client server architecture. Wait a second, let us understand this properly if we are going to study this. Okay. Gemini. explain this properly. Hybrid threading, modern systems combine both ideas, not soul mapping, thread mapping model, and modern. This is at least important from interview perspective also because thread pools. Client server architecture. When a server like web server database receives a request, it needs a way to handle it. The naive approach says create brand new thread for every request that comes in. Okay, so instead of doing anything, we create a thread and do it. But how many threads are we going to create? Creating and destroying threads take time and consume system resources. If server gets hit with thousands of requests a second, constantly spinning up and killing threads will crash the system or makes it incredibly slow. So the solution of threadful, instead of creating threads on the fly, a system will create a fixed number of worker threads when it starts. A group of ready-to-go threads is called threadful. When request arrives, it is handed to an available thread in the pool. Once the thread finishes processing the request, it is not destroyed, it returns to the pool, ready to take on the next request. And standard architecture use it everywhere, including the web server, Java, executor, and internal architecture of Node.js. Okay, so it uses it. Now, user-level threads. Threads can be managed in two different places. In user space by application itself or in kernel space by operating system. User-level threads are managed by runtime system, a thread library, or a virtual machine like JVM. Okay. How it looks, operating system does not know these threads exist. To the OS, it looks like only one single standard process running, all threads switching happening inside application itself without asking OS for help. But there is a problem with the user level threads. And what is this? Because OS only sees one big process, it manages that process as a single item. If one of your user level threads need to read a file from hard drive, the OS will put entire process to sleep while it waits for the data. Even if you have 99 other user level threads ready to do. They are on frozen because the OS blocked the single process that contains them on. Okay. So, from what I understood that OS does not know that these threads exist because these threads exist at by user, okay, by application itself, and it is managed at runtime. So as OS does not know these threads exist, it understands that there is only one single standard process is running, and all threads happens, switching happens inside the application itself without asking OS for help. But consider if it needs to read a file from hard drive or wait for network request of blocking input output operation. Then OS will put the entire process to sleep while it waits for the data. Okay, so no other processes will run until the uh, requested data is given. If you have 99 other user level threads ready to do work, they are all frozen because the OS blocked the single process that contains them all. Okay, so basically it blocks the whole working of website until it gets the requested file. Now there are kernel level threads also. These are massive blocking, solve the massive blocking problem of ULTs by letting the operating system manage everything. OS knows about every single thread. The OS connect directly responsible for scheduling or each thread. Which one kernel level thread performing blocking of input output operation, the OS knows exactly what is happening. It will put that specific thread to sleep to wait for data, but it will allow the other thread to continue running. Okay. This provides much better true concurrency, and this is why modern operating system like Windows, Linux use kernel supported threading. Okay. Now this is trade-off. User level threads are very fast, but kernel are slower. Management is managed by user library, no kernel, but it is managed by OS. It is cheap and quick, just swapping memory pointers, okay? But this is expensive, requires switching from mode to kernel mode. The concurrency is poor. If one thread blocks, whole process blocks, okay? Excellent. If one thread block, others continue running freely, okay? So this is the whole thing. It was not so difficult. So let me stick these nodes here so it will be revise. Okay, so this is the complete threading system. And with this, our client server architecture is complete. Now hybrid threading. Many users, so let's read this also. Meanwhile, we read this. Okay. As PCB is process control block, it stores process state, memory info, and resources. TCB is thread control block, it stores thread state, registers, stack pointer, and scheduling info. Its own stack, its own registers, its own PC, but share code resources. Okay, so this is important. You can stick it here. Okay. Either we can stick it here also. Okay. So yeah, this is a good place to stick it. Okay. So this is processing listed. Now let's read the hybrid threading tree. Nothing. Okay. So this perfectly follows the concepts from user level thread and kernel level thread because user thread exists entirely within your application and CPU only understand kernel threads scheduled by OS. So there has to be bridge or mapping between the two. So hybrid threading is the concept of managing this reverse also. Multiple user level threads are mapped to single level thread. The thread library handles the scheduling and switching. User space handles scheduling. The OS is completely unaware of multiple user threads. It just sees one kernel thread. One blocking call blocks all. If one user thread makes a system call, the OS blocks the kernel thread to wait for that file. Every single thread connected to it is frozen. Okay, so simple it is. If one user thread makes a system call, the OS blocks the kernel thread to wait for that file. Because multiple user level threads are mapped to single kernel thread. So if any one of the thread uh, asks for input output, then all the threads, then kernel blocks, then kernel single kernel thread gets blocked, and due to that, multiple user level thread also gets blocked. Okay, so this is the problem. This is an analogy. Imagine four workers share single company car to do deliveries. The car breaks down or stuck profit on four are stuck, even three of them. Let's try to deliver something next floor. Okay, so this is just an analogy. Now one to one. Excellent parallelism, obviously, because every single user thread gets its own kernel thread. But the trade-off kernel overhead. Creating user thread requires OS to create corresponding kernel threads since kernel thread take up. It will be the same problem that we told initially, that multiple threads will be created for multiple processes. We don't want it. Okay, so that's why we created the thread pool and all of those things. Now many to many. This is pretty good, actually. Nice. This is many to one trigger blocking IO blocked. Okay. Now this one trigger blocking IO. One is blocked, but other is running. Now this is another one. So like it is mapped with this and it is mapped with this. If this one's blocked, so it goes to here. Okay, okay, okay. This is very good. I don't know which how it is creating, but yeah. Yeah. So yeah, it is awesome actually. Uh, CS is awesome, as I always say. As an electrical engineer, I feel so much intimidated by this computer science. Okay, so living on this one's pretty good. So if you user level thread, so yeah, it is connected many user thread connected to equal or smaller number of kernel threads as we saw here. So if one of these is gets blocked, then this gets connected to previously. Like we can see, if this one gets blocked, then this goes to the second kernel. So this is the final notes that we have created about process management. Now we will study the memory management tomorrow. Okay. Yeah. So today we will study the memory management. Okay. So memory management of OS is the second part of OS after process management, and this one is smaller than the process management. Okay, so let's study memory management. So in this we study how we allocate the RAM. Let me write. We study how we Yet uh, among process among different processes. Okay, so this is the memory management. Initially, we saw how we schedule the process different in different ways. Now we study how we allocate RAM because both are jobs of operating system only. Okay, so first let's read here. Till now we have studied about scheduling algorithm. Now we will study how we divide RAM for each task. That is how we allocate RAM among processes. Okay. So main memory is RAM 4 GB, 8 GB, whatever, and it is fast memory directly accessible via CPU and volatile. Okay. Yeah, and it is volatile. It means data disappears after power off. And solid state drive is slower than RAM and it is non-volatile. Okay. So these two differences are enough for main memory and disk. Now there's different types of solid state drive SSD. Also, this is disk HDD and SSD. Okay, there are two types of memories available. This is 256 GB, 512 GB, or 1 TB. It can be anything. Okay, and HDD is slower than SSD. SSD is faster. SSD is new. Okay. Now abstract view of memory: bits, bytes, words, and chips. Memory, there are different types. Bits is the smallest unit of memory. Byte, 8 bits make 1 byte. Byte is larger than bits. And words, what are words? So word is a natural data unit of CPU, which depends on process architecture. Okay. And it depends on processor architecture. Example: 32-bit CPU, 32-bit word, 4 bytes, 64-bit CPU, 64-bit word. Okay, so yeah, let me explain what is a word. So word is a natural data unit of CPU. Remember this definition of word. And it depends on processor architecture. Like if you have a 32-bit processor, then 32-bit word makes up 4 bytes. That is the word size. Okay, so word size can be 4 bytes or 32-bit word because 8-bit makes 1 byte. Okay, so for 32-bit CPU, a word is 32-bit. Okay, word size is 32-bit. For a 64-bit CPU, word size is 64 bits. Okay, this is why my notes also show 4B, that is 4 bytes for 32-bit CPU and 8 bytes for 68-bit processor. Yeah, so here you will see 32-bit processor, byte, 64 by 8 byte. Okay, word 4B and 8. This is the width of word, 32-bit. For 32-bit it is 32, and these are addresses, and each address is of 32-bit. Okay, so basically it is 4 bytes of data for 32-bit processor and it is 8 byte of data for 64-bit processor. Now addressing. For n memory location, we require log to n bits, and here n denotes cell or word. Okay, so for n, okay, so first of all, what is a word? Word basically you can consider a cell. Like this is a one in a RAM. There consists several rows, and of each row consists of 32 columns, and each row makes up a one word. Okay, so for n memory location we require log to n bits. Okay, here n denotes the word. N equals to 16 equals to number of cells per location. Now how many bits required for these types of word? Okay, this is the minimum number of bits that is required. So how many bits we require? So for n memory location we require log to n bits. So here if we see n equals to 16, that is 16 memory locations or 16 words, we require log to 16, which is 4. Okay, so 4 bits are required. You can see here 1, 2, 3, 4. This is how 4 bits are required. Now similarly for 256 also we require 8, and for 4 GB, like it is not words, it is 4 GB. So we will assume one cell or one word equals to 1 byte. Instead of this 32 bit, we consider only 1 byte. That is a 8-bit processor. Okay. So we'll consider 8-bit processor. And for 8-bit processor or 1 byte, we'll simply get how many words? So 4 GB equals to 2 to the power 32. Okay. 2 to the power 32. You will see here that 1 GB is 2 to the power 30. So if 1 GB is 2 to the power 30, then 4 into 2 to the power 30 is 2 to the power 32. So we will get simply 32. Okay, so 32 memory locations, 32 bits memory location is required. We assumed one, but we required actually 32. Okay, so this was the thing. Similarly, this goes on. This topic explains how DIMM chips are internally organized, how multiple chips combine to make a bigger memory. So we don't need to study this because this is a part of control, computer organization and architecture. Okay. Now memory expansion techniques. So what are the memory expansion techniques? Yeah, so memory expansion techniques. Uh, we are currently leaving this topic because it is part of the digital logic and computer organization and architecture. Okay. So yeah, we are going to leave this topic. Now comes the good topic, that is program linking and loading. Okay, so this one's important, and then dynamic linking and loading. Yeah, so program linking and then dynamic linking and loading, then partition. Yeah, so mostly things we are going to study from these cuttings now. Static versus dynamic. Similarly, here we see dynamic linking and loading. Okay, so these are parts of here only. Okay, now the first thing we study is this. But before that, let's write here what we have studied till now. For n, first of all, bits, bytes, and words. So 8 bits function, 1 byte, and what are words? So 82-bit processor, 32-bit word size equal to 4 bytes. And similarly, for 62-bit processor, 64-bit word size equal 8. Yeah. So this is word depends on processor, depend type of processor. Okay. Then what we have studied, then we studied about for an memory location. Then or what? So for n memory locations, what we have we require log 2 m bits minimum. Minimum is not required. We required bits. And then we can also draw this type of diagram. Just a second. Yeah. And then we can draw and memory location. We draw our n minus x. Yeah. So this is what required, and this is what 32-bit. This is 32-bit. Okay. Yeah, this one's done. Then what we have, then we studied anything after that? I guess no. Okay, so our next topic will be this one. Next topic will be program linking and loading. Okay, so third, program linking and loading. So when we write the main function, and in that we write a, we call a function, then CPU cannot directly understand the function. Okay, it only understand memory addresses. So some function f should exist. Then we place the code into the RAM. Then replace functional function calls with actual address. Okay, this whole process is linking and loading. So linking f to RAM and then loading it. So full pipeline: program, compiler, machine code, linker, loader, access. Okay. And this is correct. So step one, compilation. Compiler converts into f into machine instruction, but compiler may not yet know where f is located in memory. So compiler leaves placeholders. Now step two is linking. Okay, so compiler may not yet know where f is located in memory. So compiler needs this folder. Step two would be linking. So linker combines my code, library code, and external functions. Example, printf is defined inside C library. Linker connects printf call with actual library code. This is called address binding. Okay. Now third, okay, yeah. So this was the thing. Now we will study about static linking, dynamic linking, then static loading and dynamic loading. Then we will know the difference between the both. So this is not a hard topic. Okay. Okay, so before studying the static linking and dynamic linking loading, first let's write what we have studied till now. So it would be um, so finding this is thing. So the entire process of finding a process function and then placing the code into RAM and replacing function for with actual address is termed as linking and loading. Now, what would be the full pipeline? So, full pipeline would be similar to program to compiler to machine code to linker loader, then process happens. Okay, so this is the full pipeline, and step one is same compilation, linking, linker combines. So what does linker do? So linker combines these things. Linker connects printf call to actual library code. This is called address binding. Okay, this is the job of linker. Okay, now let's study what is static linking and what is dynamic linking. So, static linking will be combining main function plus the function written by us together. Meaning library code copied into executables. So what is the result of it? Bigger executable, faster execution, no external dependency. Okay. Example.exe already contains printf. Okay. So this is static linking. The main plus function merged together, meaning library code copied into executables. Now, so executable will get bigger because code is copied into the executable. Okay. So bigger executable but faster execution. So we in the trade-off between memory and uh, time, we chose uh, time. Okay, so we will have faster execution but bigger executables. Okay. Now what is dynamic linking? So instead of copying library code, executables stores only the reference to library, like where the function, where I will find the function. Okay, so it only stores the library code. Instead of storing the library code, it only stores a reference to the library. Okay, so instead of storing whole thing, it just stores the reference to that thing. Now at runtime, OS loads library separately. So what in the trade-off, we chose memory over time. So here we will get slower, but we will have a smaller executable file. Okay, this is the thing. Now at runtime, OS moves example.dll in Windows and .so in Linux. Okay, so why dynamic linking exists? Suppose 100 program used printf. Static linking 100 copies of printf, but dynamic linking one shared library in RAM. Okay, so huge memory saving is here in dynamic linking. Now this was linking. What is loading? Now linker produced executables, but executables still on disk. Loader's job to place executable into RAM. So this is a thing. This was the job of linker. Yeah. So I'm currently offline. That's why the sticking thing is not coming. But yeah, we will stick it later. So linker produced the executable. Now executable is on disk. We want to place it into RAM. That is the job of loading. Okay. So loading does it. Now what is static loading and what is dynamic loading? So static loading will be load entire program before execution. So we will put whole program into our RAM. Okay. Before execution. Now the advantage would be fast execution and disadvantage will be waste RAM. But dynamic loading only loads module when needed. Example, game loads level 2 assets only when entering level 2. Okay, so this is the perfect example of dynamic loading. Now the advantage will be memory efficient, but disadvantage will be slower. Like you have to wait from level 1 to level 2. This is the disadvantage, but it is good. Considering the memory it saves, it is a very good trade-off. Now, final most important distinction. Linking resolves reference between code modules, loading, putting executables into RAM, static done before runtime, dynamic done during runtime. It was the perfect example of what is dynamic static linking. Okay. Now this is part of loading. This is job. Okay, so this was linker, this is loader. As we talked about linker and loader, now just write what is static and dynamic. So I can do this by doing this. Both is linker and loader. Both have two types. This one's static, this one's dynamic. This one's static, and this one also. What static does, so load all library code into executable in the beginning. What does this do? Only store reference to the library. Similarly, now for loading static, so it loads complete executables into RAM, okay, at once. Load entire program into RAM at once. And what this do? Load module only when needed. Okay, so yeah, this was the linking and loading. Now let's move to the next part of memory management. Yeah, this. So if we complete this, how much part we have completed of the so yeah, 50-60 pages remaining for this. Now OS memory management. Yeah, this is one of biggest OS topics. Why memory management exists? Because RAM is limited, but many processors want memory simultaneously. So OS must allocate memory, deallocate memory, protect processes, reduce wastage, and increase multi-programming. This is exactly what first image says. Main goal, suppose RAM equals to 8 GB. If OS wastes memory badly, fewer programs run, CPU stays idle more often. Okay, so if OS wastes memory badly, then fewer programs run, CPU stays idle more often. But if operating system manages memory efficiently, more processes stay in RAM, CPU utilization increase. That is better multitasking. Okay. Now there are two types of memory allocation: contiguous and non-contiguous. Contiguous processes occupy continuous memory, and non-contiguous processes split across RAM. Okay. So we know this. Now we also know our main goal. What is our main goal? That uh, if we want to manage memory efficiently so that more processes can work in RAM and CPU utilization increases. So this is done using two types of division, contiguous and non-contiguous. So if process occupies continuous memory, then it is contiguous, and if process occupies split memory, then it is non-contiguous. there are disadvantages and advantages of both the types. Okay, so we will study all those things. So contiguous allocation, example P1, P2, then pre-memory, then P3. Okay, so each process gets one block, simpler but inefficient. Okay? So simple, P1 took this part, P2 took this part, and P3 took this part. Includes overlays, partitioning, buddy system. Okay, we are going to study all of these things. First of all, what is overlay? So very old technique. If program size is greater than RAM size, like program needs 210 KB, but RAM free space is 150 KB. So it is impossible normally to do this to allocate memory. Okay. So what is the idea of overlay? Loads only needed modules. Uh, this is the same thing as we saw here, the dynamic loading. Okay. So load only needed modules. Example main A, main plus A, later main plus B, and A and B are never loaded together. Okay. So A replaces memory in same memory region. But necessary condition for this is A and B should be independent, because if A calls B while unloaded, the program crashes. Okay. Now the overlay tree is also there. The overlay tree, let me show you first the overlay tree. Yeah, so this is the overlay tree. Application 2 KB, then it calls 4, then it calls 5. So total it becomes 18 KB. Similarly, application is of 2 KB, but it calls process B, which is of 8 KB, then process H. Then similarly, it also called child processor, and we get total of these many types of sub-processors. Okay, so these are types, independent memories that is present. And what is the maximum memory size among these is 20 KB, that we must have minimum of 20 KB RAM. Okay, so it is the same thing here written. The tree shows which modules coexist. So now we compute maximum path sum. So it is a DSA problem. You must have solved it using DP. Okay. So it is a maximum path sum problem. Here DSA is used because only one branch is active at a time. Example from notes. So largest branch is 20 KB. So minimum RAM required is 20 KB. I had talked about it. Not total all of nodes. Okay, this is important. Now, after overlays, what was the second thing? It was partitioning. So what is partitioning? Dividing RAM into partition is called partitioning. So processes is placed into partitions. Two types: fixed partition, variable partition. Fixed partition means dynamic sizes. Variable partition means fixed partition means fixed sizes, and variable partition means dynamic sizes. Fixed partition, example 50 KB, 100 KB, 150 KB, 200 KB. Okay. So maximum running processes equals to max number of partition. What is the problem with this? Internal fragmentation. Example 100 KB partition. Process needs only 40 KB and 60 KB is wasted. Okay, so this is the problem with fixed partition. Like if we allocate a certain amount of RAM to a process. Example, we partition our RAM like this: 50 KB, 100 KB, 150 KB, and 200 KB. Okay. Now maximum running processes equals to number of partition, because two processes cannot enter in one partition. One partition contains only one process. Okay, so there can be only 4 processes here. Now the problem would be internal fragmentation. What is internal fragmentation? Consider a 100 KB partition. Now process needs only 40 KB, so 60 KB RAM is wasted. So this is the problem with fixed partitioning. But so now we introduce another term which is called variable partitioning. Partition created dynamically, better utilization, but creates external fragmentation. Okay, so it created internal fragmentation. This will create external fragmentation. How? Suppose free memory is 20 KB, 30 KB, 40 KB. Okay, but not contiguous. And if it is not, like from here we have free of 20 KB RAM, here we have free of 30 KB RAM, and here we have free of 40 KB RAM. So we have free RAM inside this. But since like after this a process came, since the free RAM are separated, so one process of 80 KB cannot run on this. Okay, So we protect it using base or limit registers. Uh, we can do this. It I have written here. This part is important. Suppose P1 allocated 100 KB to 200 KB. Okay, so this is what? This is just considered a memory address. So 100 KB from 100 KB to 200 KB address is allocated to P1. Process 1 will take only the address from 100 KB to 200 KB. It cannot take ahead of this. It cannot take uh, behind like memory previously from 100 KB before 100 KB. Okay. So it means P1 is allocated memory from 100 KB to 200 KB address. It should not access any address beyond its 200 KB address. So how we write it? Base is equals to 100 and limit is 200. Now suppose if process access 200 KB, hardware traps error because it has been allocated only in 200 KB. So this base or limit registers helps to prevent one process from corrupting the another, and that's why uh, it is also not possible to like here if a process has been allocated, here also we can say if process has been allocated from 0 to 100 KB, from 50 KB to 100 KB, then we say that yeah, it is good. So process cannot access any memory beyond 100 KB. So the free memory will be like separated, and it will be not contiguous, and it should not access. This is protected using base or limit registers, that it should not access any memory beyond this. Otherwise, someone will have got access of address and can erase it. Okay. So this is the thing. Now, what is non-contiguous allocation? This was contiguous allocation. This is non-contiguous allocation. This is modern OS memory management. It includes paging, segmentation, and virtual memory. Because contiguous allocation has fragmentation problem, modern system mostly use paging plus virtual memory. So what is the important picture? Contiguous allocation, then fragmentation problem arrives, then we use the non-contiguous methods like paging and segmentation, then virtual memory. Okay. This was the whole story of uh, this memory management. Okay. So from now we will study the problems that happen. Fixed partitioning versus variable partitioning. The problems why fixed partitioning is bad, performance of fixed partitioning and then performance of variable partitioning, the partition control memory. Okay. Compaction or coalescing. Okay. Then we will have these examples. Then we will study the paging. Yeah, so this is important. Paging is like the important part of memory management. From now on, it is only paging and paging. Okay. So this whole thing will continue of paging. Then we will study the segmentation. It is another part of the non-contiguous memory allocation. Okay. So this will be segmentation, but segmentation also consists of paging. Okay. So yeah, main thing we are going to study here will be paging, only page fault and the name. So here we'll see a formula also. Let me see what all the contents will be. Then if RAM becomes full, which page should remove OS here also. Then we'll see the page replacement algorithms here. So this is also important, but it is easy. Okay. Then we will study the Bernardi's anomaly. Okay. Uh, is there anything? Yeah, next is thrashing. So thrashing is also one concept. It is also related to aging. Okay. Yeah, thrashing is also a thing. then complete. Okay. So yeah, we will study till here, which what page it is? 276. 276. Not much left then, I guess. 276 is the final page what we are studying. Then yeah, we are already at 227, I guess. Yeah, we are at 227 now. We have completed the 227, so we can move ahead. Yeah, so we have seen these things. We'll just make notes of this. Which is 225. Okay. After making notes, it will be completed. Yeah. So next, what we have the OS memory management property. We have studied it. Now just note making is left. So OS memory management. It has two parts. One is contiguous. Second is non-contiguous. Third one, contiguous memory allocation. Okay. So for the contiguous memory allocation, um, it includes what? One, it include one word is two partitioning and three buddy system. So first, what is over there? It is load modules only when needed. Okay. Now the second would be fixed and variable. And variable. So fixed, this causes internal fragmentation. Okay. Yes, internal fragmentation. And this causes external fragmentation. Okay. So these are the two things. And this is what internal fragmentation is. Now, what is external fragmentation? So this will be external fragmentation. Okay. Now, protection using base limit and register. So there is also a topic I will it here. Do that limit register. What is this? This is it. Okay. Now the second would be the non-contiguous allocation. Okay. So non-contiguous allocation. So it includes what? It includes one paging to segmentation and the virtual memory. Okay. So yeah, these are the three things present in the non-contiguous memory. It is modern OS management. Modern OS memory management technique. Okay. So yeah, it is this. This is evolution. Now we can study about paging in depth. But before that, we'll also study the fixed and variable partitioning in depth. This is just for understanding part what happens. Okay, so let's understand what happens. So RAM is already divided into fixed blocks. Example 50 KB, 120 KB. Okay, processors must fit into one partition. Allocation strategy. Suppose P1 is 75. So first fit would be whichever waste, wherever waste is very less, we will add it to that. Okay, so first fit, the best fit, and the worst fit. Okay, now what is fragmentation? So suppose fragmentation is important, but there are two types: internal and external. Partition 50 KB, process 40 KB. So unused is 10 KB. This waste is inside allocated blocks. So internal fragmentation. Okay. External fragmentation. Suppose free blocks 120 KB plus 80 KB, total 200 KB. New process 200 KB still cannot load because memory is separated. This is external fragmentation. Okay. Imagine RAM like this. Process enters one memory after another. Load process P1, P2, P3, P4, everything continuous. No issue. Step 2. Suppose P2 finishes, P4 finishes. Now the memory becomes free. P2, P3. The free memory is split, not together. Okay. Suppose first free block 100, second is 250 KB. New process 200 KB. Can OS load it? You may think yes, because 250 KB is free, but no, because process needs one continuous block, but blocks available are in two parts, so neither can hold 200 KB. So this is external fragmentation. And why it is called external? Because waste is outside allocated process. So yeah, this is the total thing, the best fit, worst fit, and first fit. These all three are important. What is partition control memory? So the table stores like this PID, LL, UL size. LL is lower limit, UL is upper limit. So it tells from where to where I have been assigned the memory for this process. For tracking memory protection and allocation. Okay. Suppose P6 equals to 43 KB, first free block 45 KB, remaining 2 KB. Best fit. Choose the smallest total. Worst fit. Choose 350 KB. So 307 KB is best. This is good strategy for variable partitioning because large holes survive. Okay, so yeah, it is one of the trick that if you do the worst fit, then another process can enter into it. But if we leave only small chunk of memory like just 2 KB, then no process can fit. But in 307 KB, processors can fit. So it will be a good thing to allocate memory according to the worst fit instead of best fit or first fit. Okay. Now performance of variable partition. And yeah, this is what is done in variable partition. Performance of variable partition, no internal fragmentation, but because exact allocation, but external fragmentation exists. Process finish at any time, holes appears, example P3 complete, now memory becomes free hole free. Scattered memory. So the solution would be comparison or coalescing. OS shift processes together before P1, P2, P4, P5. Now after that, these are together and the free memory are merged into one large block. Now 385 KB contiguous available. But this is expensive because OS must move processes, update memory addresses, pause execution sometimes. So it is costly. So this is the final big picture. Fixed partitioning, fixed blocks, internal fragmentation, simple, limited processes, and easy management. But variable partitioning is dynamic blocks, external fragmentation, flexible, more processes, complex management. Okay. So yeah. Okay. So yeah, this is the perfect definition of external fragmentation. Now this is what best fit, worst fit, and first fit is. This is partition control memory. Okay, so this is important. This is variable partitioning. We have seen this. Why fixed partitioning is bad? Because degree of multi-programming fixed. Because if five partition exists, max to max five processors. Even if RAM still has unused space, so process size limitation. 500 KB cannot accommodate because largest partition size is smaller than 500 KB. Okay. Now, variable partitioning, partitions dynamically, partitions created exactly of required. But because variable partitioning is a good topic, so we are going in depth. Yeah, so this is complete thing, but I should also write this point that is compaction is expensive. Final big picture, this would be the thing. Okay, so compaction is expensive. Now this part is completed. Now we can start with uh, paging. So the most important memory management topic in operating system. 40 pages remaining, max to max 40. Okay. In this 40, we will see max to max 7 to 8 pages. Okay. And in 7 to 8 pages, we will complete everything. So see you after some time. So now, what is paging? Okay. So what we were learning before, continuous allocation. Processes need one continuous block, and the problem was like external fragmentation. Okay, so the continuous allocation has two types: fixed partitioning and variable partitioning. Now we will study about non-contiguous allocation. And the first concept in non-contiguous allocation is paging. First, let's understand the main idea. Earlier, processes must be stored continuously. Problem with that, free memory becomes scattered, which is either uh, what you can say internal fragmentation or external fragmentation. Both have the same error that free memory becomes scattered. Now, paging says who said processes must be continuous. So instead of dividing memory, why can't we divide the processes? Okay. So we split the process into small equal pieces. This is the entire idea. Then two important terms that comes here is pieces, pages and frames. Pages are pieces of process and frames are pieces of RAM. So the very important relation what we get is page size must be equal to frame size. Then we can say that all processes can complete. Okay. For example, process size is 8 KB, page size is 1 KB, then process becomes 8 pages like P1, P2, P3 to P7. Okay. Each of 1 KB size. Then RAM, suppose RAM is 4 KB and frame size is 1 KB, then RAM becomes this. Now, process pages can go anywhere. Example, page 0 can go to frame 2, page 1 can go to frame 0, page 2 can go to frame 3. No continuity needed. So this removes the problem of external fragmentation. But then huge problem appears. Say CPU says give byte at address 2500. But since process is scattered, so how will OS know where the actual data is in the RAM? Okay. This is why page table exists. Now what does page table do? It maps page number to the frame number. That is page 0 has gone to frame 2, page 1 has gone to frame 0, or page 2 goes to frame 3. Okay. Meaning page 0 is stored in frame 2. So address translation. Now we can do the address translation. Like here you see we said give byte at address 2500. So CPU generates logical address, like first it generates logical address that it is present in the frame 2. Then it generates like even in frame 2 it is present in this part, after this part. Okay, so it generates a logical, we will read what the logical address here will be. But RAM understands physical address. So MMU converts logical address to physical address. Okay. So MMU is a thing which converts logical address to physical address. We have seen this in the start of our chapter. Okay. Now the most important part. Yeah, this is the most important part. How logical address is converted to physical address here. So logical address is split into page number and offset. Okay. Example, suppose page size is 1 KB. So 1 KB we know it 2 to the power 10 bytes. Okay. So offset needs 10 bits. Now offset needs 10 bits because suppose logical address is 13 bits. Then 3 bits will be page number and 10 bits will be offset. Okay. So we will understand this because page can be maximum 8. We have seen that page is 8 here, P0 to P7. So 2 to the power 3 equals to 3 bits maximum. So 8 is equals to 2 to the power 3. So we max to max require 3 bits. And as size of each page is 1 KB. So 1 KB is 1024 bytes. So we can need any byte of 8, like 503rd byte. So offset will be maximum of 1024 or 10 to the power 10. So 10 bits. So by 10 bit we can get to any number between 0 to 1024. Okay. Now the more explanation is given in next page, but I have explained you how everything works. Okay. We will read this also. So offset needs 10 bits because it needs to go to tin address 10 to 1024. Okay. Suppose logical address is of 13 bits. So if logical address is of 13 bits, first 3 bits would be page number and next 10 bits would be offset. Why 3 bits? Because pages is 2 to the power 3. I have explained. Okay. Now the translation process. CPU gives page number and offset. Example 2, 500. MMU checks the page table. So for page 2 go to frame 3. Now address become frame 3 offset 500. Done. This is the physical address. Okay. So we converted the logical address to physical address. And high paging is revolutionary because processes do need not to be continuous. External fragmentation removed. Memory utilization improves. Virtual memory becomes possible. Okay. These are the advantages of paging. And this is the foundation of modern OS, cache, virtual memory, page replacement, everything come after this. Okay. Now I had doubt. I have even said that I did not understood that while I was studying. So yeah, I have explained you this properly how everything works. Yeah, so this is the whole part I have explained you. Now we can move to the next part. Now why TLB is needed and why paging becomes slow, because first we have to convert the logical address to physical address. We have to also maintain a table Okay, so first remember normal memory access. Without paging, CPU directly accesses RAM, CPU RAM. Suppose one RAM takes m nanoseconds, then memory access time equals to m. Simple. But with paging, CPU cannot directly access RAM because logical address must first be translated. So now CPU page table lookup actual RAM access, meaning two memory accesses happen. Okay. First access find frame from the page table. This itself is stored in RAM. So one memory access. Okay, so instead of directly accessing the CPU, uh, it instead of directly accessing the RAM, it now first do page table lookup, then do actual RAM access. Okay, so first access find frame number from page table. This itself is stored in RAM. So one memory access. Now the actual data is fetched from RAM, then again one memory access. Okay. So first we will find the page frame number from page table, and since page table is stored in RAM, so it takes m nanoseconds. Okay, and similarly here now actual data is fetched from RAM. This again takes one memory access, so 2m. So m plus m 2m. This is effective memory access time. Okay, so EMAT is 2m for paging. Why this is bad? Because paging doubled memory access time. System becomes slower. So operating system plus hardware engineer invented TNB. What is TNB? Translation look aside buffer. You can understand this as a cache memory. This is tiny super fast cache as it is written here. So it will first it stores recent page number to frame number mappings. Okay, so instead of looking to whole table, it look aside a buffer memory. Okay, and in the buffer memory, it fetches it. But the buffer memory is works on probability. So this is what we must know, that buffer memory works on probability. You can get your desired page number, or you can not even get your desired page number from this. So yeah, now what happens is processors often use same page repeatedly. So instead of going to page table every time, check TNB first. If TNB hit, okay, so there are two possibilities, TNB hit or TNB miss. Okay, so TNB hit and TNB miss. Then CPU, TNB, damn, no page table access needed, so only M. The time taken is M. Okay, so it'll be only TNB lookup and RAM access, so it is fast. But if TNB miss happens, then TNB miss, page table in RAM, and RAM access. This is a slow path. Now, why cache TNB hierarchy is shown? Because computer memory looks like registers is fastest, then N1 cache, then N2 cache, then RAM, then this. This is the slowest. TNB is another fast memory near CPU. Okay, now you will see the probability thing also here. Okay. Is probability thing not mentioned here? Yeah, I guess it has not mentioned the probability thing. Yeah, it has mentioned. Okay. So probability thing is mentioned. X is probability here. X is TNB hit ratio, that it will hit or not hit. So this whole sum is of probability. Okay. So we will study this now. So how to reduce page table size? So we have already understood the paging, page tables, and TNB. Now the next big problem is with simple paging, logical address space. Consider logical address space is of 4 GB, page size is of 4 KB, and each page table entry is of 4 bytes. Okay, so uh, for 4 GB, that is 2 to the power 32, and each page size 4 KB. So number of pages would be 2 to the power 32 divided by 2 to the power 12, so 2 to the power 20. So 10 million pages. Each process needs 1 million page table entries. Okay. For one process, 1 million page tables is created. Like 1 million pages is there, so each process will need 1 million page table entries. Okay. So page table size would be 2 to the power 20 into 4, so 4 MB, okay? Meaning every process needs 4 MB only for page table. Suppose if 10 processes run, so 10 into 4 MB equals to 40 MB, huge waste. This is the first thing, okay? Now, yeah, we have seen here that suppose if every process needs 4 MB only for page table. If 10 processes run, then 10 into 4 MB equals to 40 MB. So we see that the page table, since there are 1 million pages, so 2 to the power 20, and each page table size is of 4 bytes. We have seen here each page table entry size, page table and each entry is of 4 bytes. So total page table size becomes 4 into 2 to the power 20, because there are 1 million page entries. Okay. 1 million pages, each process needs 1 million page table entries. Okay. One million pages, like, so for more clearing, like P0, P1, P2, P2 to the power 20 minus. Okay. So yeah. So this needs 1 million page table entries. And each page table size is 4 bytes, so 4 into 2 to the power 20 is 4 MB. Every process needs 4 MB only for page table. If 10 processes run, 10 into 4 equals to 40 MB, huge waste. This is the first thing. So first attempted solution would be increase the page size. If page size becomes bigger, number of pages decreases, page table size decreases, good. But now another problem appears, internal fragmentation. Okay. So if we think to increase the page size, and why would we need to increase the page size? Because every process needs 4 MB only for page table. So every process needs 4 MB for page table separately. Like if every process requires 4 MB and 10 processes run, then 40 MB of space is taken by page table only. Okay. So this is a huge waste. Okay. Now first attempt would be to increase the page size. If we increase the page size, then the division would be low. Number of pages will become less, and so page table entries will also become less, and page table size will also become less. Okay. But if we increase the page size, then again the same problem would happen of internal fragmentation, just like we saw in the fixed partitioning. Basically, creating pages is just like fixed partitioning only, but just with a smaller parts. So if we do fixed partitioning with smaller, but we were doing first fixed partitioning in RAM, but here we are doing fixed partitioning of process and RAM both. Frames is of RAM and pages of process. Okay. So internal fragmentation would happen. Now suppose program size is 1026 byte, so page size is 1 KB. 1024, so we will need one full page and second page for remaining 2 bytes. So waste would be 1022 bytes wasted. Okay, so we cannot create a we cannot create this much of thing, because for the second page 1, so page 0, page 1, for the frame 1, I should say frame 1, in the frame 1, 1022 bytes wasted. So this is a huge internal fragmentation. So we want the page size to be, yeah, page size and frame size is almost kept same. Okay, so if page size is this, it will take one full page. Now second, yeah, it will take one full page, 1024 bytes, and second page for remaining 2 bytes. So in the second page, this 1022 bytes will be wasted if we increase the page size. But suppose if the page size would be low, then what would happen is that uh, it will be less wasted, because suppose if there will be 512 KB, then 510 KB would have saved, would have wasted. So 510 is obviously less than 1022 bytes. Similarly, if we keep getting smaller, then it would be better, less memory wastage, but it will be uh, it will take more memory, like every processor will need more memory. So we also need to increase the page size, but increasing page size also means the wastage of memory. Okay, so yeah, there should be a trade-off, because increasing page size is a solution of wasting less memory, and increasing page size also wastes memory. Okay, but why this helps? I guess it is of second part. No. So, larger page size, smaller page table, but more internal fragmentation. Okay. So this is a trade-off. Optimal page size formula. So this is a formula which tells us optimal page size. Instead of 4 KB writing directly 4 KB, we solve it using this formula where P equals to root 2 SE. Where P equals to root 2 SE. P is the optimal page size, S is the process size, and E is page table entry size. So it is not very important conceptually for GATE and interview on GATE, but yeah, we should remember the optimal page size formula. It is root 2 SE, where S is process size and E is page table entry size. Now the real solution would be to use multi-level paging. So this is the main concept now. Original idea, one giant page table. So we will now break it into smaller page tables, like folder inside folder. So in simple paging, logical address look like first page number, then offset. Now in two-level paging, it will look like P1, then P2, then D. Instead of directly indexing one huge page table, P1 used to find the outer page table entry and P2 used to find inner page table entry. Then they get framed combined with offset. Think of it like city street first. Yeah, instead of one massive global address list. So yeah, it is not so difficult to understand. We will write uh, the notes. Yeah, say we have arrived on segmentation now only. Yeah, it's only 20 pages after this. Okay, so we are close to ending this. Much time. Yeah. So why this helps? In simple paging, one entire huge table page must exist. In multi-level paging, only needed inner page tables are created. So huge memory saving is there. Now the example from image we see is 20-bit page number plus 10-bit offset. So they split it this 20-bit page number to 10 and 10. So 10 would be P1, 10 would be P2, and then the offset would be 12. Find which inner page table to use. So P1 will tell which inner page table should we use. P2 will tell which exact page entry inside the inner table. And page step 3 will get us the frame number, the offset. Okay. Now high performance becomes worse. Now memory accesses increase. Even though we have saved the memory, but the time becomes worse, because now one access is required for page table, one access will required for the actual data. So total is 2M. Now for the 2-level paging, it will be 3M. For n-level paging, it will be n plus 1M. Okay. So in simple paging, it is 2M. For 2-level paging, it is 3M. And for n-level paging, it will be n plus 1M. So again, problem appears, multi-level paging is slow. Hence, TNB is used again. We have seen the TNB. It is just like a cache. So multi-level paging plus TNB. If TNB hit occurs, translation found immediately, which is very fast. Walk through all page tables. The formula in the image is this. Yeah, we have seen this formula. So C is TLB access time, M is RAM access time. So C will be constant because it is the time taken to access the TLB. Okay. So we are always accessing TLB. So X equals to C plus M, where X means hit ratio, that currently it is hit. And if TLB is hit, we need only one RAM access. So it is only M. But if TLB is not hit, 1 minus X, then we will need 3 RAM access. So C plus 3 MC will be always constant. Okay. So interpretation, what is interpretation? TLB hit probability equals to X. Now TLB access plus memory access. Yeah, we have talked about. Now the last topic would be hashed paging. It is used for large address spaces. Instead of giant page tables, use hashing. So what does hashing do? It's just make the small things and large things smaller. So if you have studied about the hashing concept in DSA, then you would have known that how we convert a very big string into a small number, and that number is unique for that string. But there is the problem of collision in the hashing. Okay, I guess here also that problem with the peer. So hash pages is used. Similarly, we saw what is hash maps. Okay, so not let's not get diverted. Very large address space, 64-bit system. Instead of giant page table, use hashing. So main idea would be logical page number P, apply hash function, go to hash table bucket, find matching page table entry, get frame number, construct physical address. So this is used in large address spaces like 64-bit system. And why it helps? Because for gigantic address spaces, normal page tables become absurdly huge. Okay. Hashing avoids storing massive, mostly empty tables. So this was the thing. Before segmentation, we will write some notes here. So yeah, 2 pages, then 4 pages, yeah, then 8 pages, then 10 pages. Okay, so before segmentation, let's finalize what we are going to study now. What we have studied till now. Okay, let's write the notes properly. Okay, so let's make the notes now. We have not written anything about paging, so let's write about paging. A would be paging. Yeah, it is worth it to write and read because it is the main topic of memory management. Okay. Hmm. Yeah, so this whole thing is okay. So I should include this also. These notes are really awesome to understand. It's easy. Okay. ChatGPT have made studying so easy. And now, yeah, so let's continue. Instead of writing like this, we can just write yes, process. Instead of writing, we can just stick the part also. Okay. We can stick, and according to that, we can make that page table also. So page table becomes like okay. So this is the page table. This removes the external fragmentation, but uh, the external fragmentation is too bold. We should not hit this removes. Okay, what it removes? Okay. So yeah, this removes the external fragmentation. Then huge problem appears. It maps page number with frame number. Okay. Yeah. So now, mm, yeah. So after this, data is in RAM. This is why page table exists. So after page table, we seeing this. What is logical address? It is like go to address 2500. It is a form where it is page number and this will be offset. How this works, we have talked about. Now just note making is left. This is the complete thing. Let's take a screenshot of this. Okay, so this is the thing. The return address is split into page number and offset. Suppose page size equals to 1 KB equals to 2 to the power 10. So offset needs 10 bits. Suppose the return address 13 bits. So this is the thing we have talked about all of this. We are just making the notes now. So yeah, for notes it is perfect. Becomes good. Because CPU to page table to RAM. Also, we must know that we must know that this page this page table also exists in RAM only. Okay, so this is the first point. Okay, so this is the 2M is the total time. Just a second. Yeah. So 2M is the total time, then we exist. Yeah. Now I can continue. We have talked about this, so we will use TNB. So to decrease the time, we will use TNB. What is TNB? Just a small gas which stores frequent page. What was it called? Page rows. What? Let me first confirm. No, not this, but here isn't here written anything about memory. Yeah, so I guess we have studied too far that memory consideration is not out here. Yeah, so page table entries. Okay, so we will use TLB, frequent page table entries. Okay. Before TLB, EMAT. And what is EMAT? Effective memory access time was 2M. Okay. And why this is bad? Yeah, so this is why it is bad. So now after TLB, two possibilities. One, TLB at equals to M. And second would be TLB EMAT will be 2M. Okay. TLB hit and TLB miss. Two possibilities are there. Problem with simple paging. So this is the problem. Now the first attempted solution would be to increase the page size. If page size becomes bigger, so first attempt would be to increase page size. So if we increase not page table size but page size, okay, page table size would be same, that is this will be 4 KB only. No, this will be 4 MB only, but page size will increase. Page size, if we increase the page size, yeah, the page table size also decreases. Okay, so page table size decreases. But it causes internal fragmentation. And how? This is the example for it. Okay, so yeah, this is the thing. And why this helps in simple paging, entire huge page table must exist. In multi-level paging, only needed inner page tables are created. So the solution would be, okay, no, we have diverted from the idea. Now the optimal page size formula is also, yeah, so smaller page tables but more internal fragmentation. So there is trade-off with this. So optimal page size is used. So the second and real term would be multi-level paging. What is this? Instead of one giant page table, we divide it into two parts. Okay. So this is the idea. Now, why this helps? In simple paging, huge page table must exist. In multi-level paging, only inner page tables were created. So memory is saved from both aspects. We create one big table also, and then we make it even smaller. Okay, but the trade-off will be time. Benefit. is for EM80. It will be N+1M for N naval paging. Okay, so this is the thing. So we'll use TLB again. So this was the total multi-level paging concept. Okay, I think I should uh, write the whole thing in left side. Lefter is better. Okay. So yeah, this was multi-level paging. I have explained you this part. Now we will study the next part, which is segmentation. Okay. So why segmentation was invented? So paging solved the external fragmentation, but paging destroyed the user logical view of program. Program with paging. So suppose program has main, function f, g, global variables, stack, heap. To you, these are separate logical units, but paging cuts memory into equal parts, that is P1, P2, P3, P4. So main may split across pages and F may split across pages. So program structure gets lost. This is what it mean by user's view is not preserved. Okay. So what user sees is main and F, but what computer sees is different parts of main and different parts of F. So user's view is not preserved. It is what does it mean? So segmentation idea. Instead of equal size pages, divide program logically. So S not. So if we till now we have divided programs in pages, but now we will divide it into segments. So S naught will be the main, S1 will be the function F, S2 will be the function G, S3 will store the stack, S4 will store the heap. Okay, so each segment can have different sizes. Now the very important difference, paging equal size physical view, uh, pages, frames in RAM. Okay, segmentation is variable size because main can be bigger than function F. Okay. Logical programmer's view and segments contiguous block. Logical address in segment is PD, so now it will be HD, segment to offset. Instead of page table, we will have segment table. So yeah, this is another method. Now the translation in segmentation, segment equals to 2, offset equals to, so it will be say go to H2 base 1500. Okay, this is same as table paging. But problem with segmentation, segments are variable size. So RAM gets whole again means external fragmentation returns. So final combined solution will be segmented paging. This is paging inside each segment. Okay. So it is very good concept. Like we preserve the user's view and then we also perform the paging inside it. So the function does not get distributed and we also uh, remove the external fragmentation things. So now the how the address would look like. So it will be look like SPD. Okay, so yeah, SPD logical address becomes SPD now. Now the translation process will be same to go to segment S, go to page table of that segment, use page number, find frame number, then combine with offset and get physical address. Now this is very powerful because local organization from you get local organization from segmentation, no external fragmentation from paging. Okay, this is why real system move towards paging the segmentation combined. Now paging the segment table. Now another problem appears. If many segments exist, huge segment table exists, then segment table itself become huge. Okay. If many segments exist, then segment table becomes huge. Even segment table is paged. This is another optimization, not conceptually different. Yeah, so I don't know what does it mean. Okay, so let's leave this. Now the final topic will be virtual memory plus demand paging. This is extremely important. So the core idea is process thinks it has huge memory, but only some pages are actually in RAM. Rest stay on disk. Okay, this is the thing. So this was the core idea of it. Like we use virtual memory and demand paging. We only demand those pages which we require. Otherwise, everything stays in the disk. So this saves the RAM too much. Okay. Now the virtual address space is 8 KB. Physical RAM is 4 KB. Means whole program cannot fit into RAM. Okay. But OS still run it. How? Using virtual memory. Key idea. Only currently needed pages are loaded into RAM. Okay. The remaining pages stays on HDD, SSD, swap space. Okay. So example from image is pages are divided. Some are in RAM, other remains on disk. So page table now has valid and invalid bit. Bit one denotes page present in RAM and 0 denotes page absent. Okay. CPU generates PD page table checked if valid bit page exists in RAM. Normal translation if invalid bit or 0 bit then page is not exist in RAM. This causes page fault. Then OS does pause process, load page from disk to RAM, update page table and restart instruction. This is demand paging. Okay. Now the problem with this would be again this will make the program slower. Okay. So because the time from loading page from disk to RAM will take time. But we are only doing it because we have less memory. So the trade-off is always again we trading of our time to manage our memory. Okay, this is the thing. Now we will see page fault handling plus demand paging performance. So what happens during a page fault? If we know that page is not in the RAM, then what happens? OS must bring page from disk to RAM. Why this is expensive? Look at memory speed hierarchy. Okay, yes. So disk speed is extremely slow compared to RAM. So the difference is massive. Now the page fault service. Suppose process 1 wants page 1, but P1 is not in RAM. Then step 1, current process blocked, CPU cannot continue execution, process enters block or waiting state. Step 2, CPU enters kernel mode because OS handles memory management. Step 3, OS virtual memory manager starts working. It must locate page on disk, bring it into RAM. So case 1 would be empty frame exists in RAM. This is easy. Suppose RAM has one free frame. Then copy from disk to RAM, update page table, set valid bit 1, restart process. Okay. Case 2, no empty frame available. Like RAM is full. Then what will happen? If RAM is full, then we cannot add. So we must remove some existing page from the RAM. This is page replacement. And the page that will be removed is called victim page. Okay. Which page should be removed? It is decided using the page replacement algorithms FIFO, LRU, MRU, optimal. Okay. So also there are types of pages like dirty page and clean page. Clean page, page not modified after loading. So original copy exists on disk. meaning no need to write back. So after we have loaded the page into the RAM and suppose it does not change anything, the page remains same. That is the function. Suppose function is bring into RAM and we do not change the function. So function remains same. So original copy exists on disk. It does not needed to change it, meaning no need to write back. Can directly remove it. Okay. So can directly remove the victim page. It is fast. Now the dirty page. Page modified in RAM, disk copy is outdated. So before removing, we must write the updated page back to disk. So this is extra disk operation and this is slower. So replacement steps become, if dirty, write victim page to disk, then load new page from disk. So this is two disk operation and this is very expensive. Now the demand paging would be of two types, pure demand paging. So this is the default modern idea. Initially, no page is loaded. Page load even required. Okay, meaning first access calls page fault. Then we do pre-paging and pre-fetch paging. So OS predicts that some pages will be needed in future. So it loads them beforehand. The goal is to reduce the page fault. And what is the page fault? That founding of page in the RAM is not. Okay, so it reduces the uh, page fault because OS predicts that it will be needed. So if it already is loaded, then page fault decreases. Okay. Now comes important formula EMAT. So how the effective memory access time would look like. So key observation, page fault time much larger than RAM access time, obviously because it involves disk. Okay. So if it involves disk, then it is too much time. So the formula intuition, we don't need intuition, we can directly write it. So probability of fetching the memory equals to S plus 3M. Like if the memory is to be fetched from disk, it means like we don't have the page in RAM. Okay. So P plus 1 minus P, 2M if page exists on RAM. Okay. And 2M high because TNB is also used. So multiple concepts are used here. Okay. Now the most important formula, even very small page fault rate can destroy performance because S is huge. As I already told you, it is very huge. So this is just an example. Okay. We don't need example. We can directly say. So page faults are extremely costly. So the final intuition, RAM access very fast, page fault extremely slow, too many page fault, thrashing. Okay, so too many page faults is called thrashing. Speed is thrashing. Speed is thrashing. Okay. Let's go further. Now, how does this whole thing works? So, is there anything after this also? Yeah, it is. So we have reached to end. There is 4 and 6 pages. We have already studied the 4 pages. 6 more to go. So if RAM becomes full, which page should OS remove? This that is the page replacement algorithm. So first a page reference string is generated. Suppose process accesses pages in this order. 7, 0, 1, 2. Okay, so pages are process access pages in this order. This sequence is called page reference string. Okay, meaning order in which pages are requested over time. Now the sample setup, suppose frame equals to 3, RAM can only hold 3 pages at once. Now pages arrive one by one. If requested page is already in RAM, so page hit will be happen. Otherwise page fault will occur and this will take time. So if RAM is full, now we need to replace some pages from the RAM to make the new page comes into the RAM. Okay. So now the frame allocation policy. Suppose RAM has M frames in total. How many processes running? And suppose RAM has M frames in total and many processes are running. How many frames should each process get? Okay, so this is also a problem. Suppose if the frame size is smaller than the process size, so we will need to increase the instead of process we should say page. Okay, so if frame size is smaller than page size, the page size that we want to put it into the work. Then how it will be allocated? Equal allocation. If 40 frames, 5 processes, then each get 8 frames. Each process will get 8 frames. Okay, simple. Second would be the proportional allocation. A big process should get more frame technically. Okay, so if in 5 process there are multiple sizes of process, like some is of 80 KB, some is of 50 KB. Then suppose 8 frames is not able to accommodate the 90 KB process, so it will not work properly. So here we will have error in equal allocation. So we will use the proportional allocation thing. Okay. So big process will get more frame. So it will get more frame by like this. Okay. Now the important part, page replacement algorithm. So FIFO, first in, first out. The idea is to remove the oldest loaded page. So we always already know what FIFO, LRU, LCO, these are things. Okay. So FIFO advantage is simple, but FIFO problem is Berardi's anomaly. So what is Berardi's anomaly? Sometimes in frame increase, sometimes increasing frames increases page fault. Okay, how is this? Like if we increase the frame, we will have increased page fault. That means the page is not present. And yes, this is true, because if you will think about it, you will find that giving one process or yeah, one page more frames, it means the other frames get the other pages get less frames, and some pages would miss out, and those will who will miss out will cause page fault. So the page fault will be more because the pages entering in the RAM would be less. Okay, so simple these things. This example is same, like 3 frames 9 faults, 4 frame 10 faults. More memory but worse performance. Okay. That is Berardi's anomaly. I hope so. I am explaining it right. 3 frames 9 fault, 4 frames 10 fault. Is it explaining anywhere? FIFO problem, Berardi's anomaly increasing. More memory but worse performance, that is Berardi's anomaly. So optimal replacement, theoretical best algorithm, remove pages that will be used farthest in future. So we cannot decide the future, but that's why it is theoretically best algorithm. So remove page that will be used farthest in future. So if we remove the page that will be used farthest in future. Okay. So Benardi's anomaly can also be like this. Uh, if we increase the frame size and we try to replace the process, but that process comes multiple times. Even in FIFO, it comes in future multiple times. Then that will increase the page fault because we have removed it. Okay. So let's like, understand Benardi's anomaly properly. Okay. Let's not guess. Instead, let's try to learn what is Benardi's anomaly. Even I get confused sometime. Okay. Let's until it generates the answer. Let's look at the things. Why optimal is best? Because it minimizes future page fault. So this is the optimal replacement, and but why not use? Because OS cannot predict future. Okay. Now the next algorithm would be to use LRU. So this one's is algorithm. Okay, just like FIFO was algorithm. This is also an algorithm. It is not to counter Benardi's anomaly. Okay. LRU we know the least recently used. locality of reference. If page used recently, likely used again. So it is based on the locality of reference. NRU exploits this. NRU implementation, okay, needs to track the whole history. We implement the NRU in the lead code. There is a problem of NRU and okay, NRU problem. That is, I guess, LD problem, low level design. So yeah. Next, we see the stack algorithms. Important theorem. For stack algorithms, pages with n frames are always subset of pages with n plus 1 frames, obviously. Meaning more frames can never worsen. Yeah, so if we have already uh, n plus 1 frame process, then n frame process can simply replace it because it is smaller than the current n plus 1 frame process. More frames can never worsen. So which algorithms are stack algorithms? Optimal and NRU. Therefore, no Bernardi's anomaly. Now the MRU most recently used, it is opposite of NRU. Remove the most recently used page. Usually worse but useful in some sequential scans. Okay. Now the counting algorithms. LFU least frequently used, MFU most frequently used. These are also can be used. Okay. NRU approximation. True NRU is expensive. Okay. So OS uses some approximations. How is this? Also, this is very important for interviews and exams. So how it does these things by reference bit, R bit. Every page has R equals to 0 or 1. If page accessed 1, okay, if page is accessed then R equals to 1. Periodically, OS resets all R bits to 0. This period is called epoch. Oh, okay, epoch, I guess you have seen this term in machine learning. So periodically OS resets all its R bits to reference bits to 0. So this period is called epoch. Idea. Pages with R equals to 0 not used recently. So these are good candidate for replacement. But problem, what if all reference bits equals to 1? All reference bits equals to 1. We need better method. Okay. If all reference bits is 1, then we cannot use the R equals to 0 thing. So we will need a better method. So second chance lock algorithm, super important practical algorithm. So this is a practical algorithm and it is used widely. So the idea is FIFO plus reference bits. Pages arrange circularly like lock. So OS pointer move around. Replacement row. If page has R equals to 0, replace it. If R equals to 1, give second chance. Okay. Set R equals to 0. Skip page, move pointer ahead. Why it is called lock? Because pointer rotates like lockhead. Why good? Cheap approximation of NRU, very popular in VLOS. So 11 would be enhanced secondary. So first let's look at this what this says. Okay. So it says that it uses FIFO, first in first out. That is the older one gets removed faster. So it says older one, the one which came first, okay, not the older one. The one which came first will be removed first. Symbolizes recently used or not. Okay. So pages arranged circularly like a clock. OS pointer moves around. So if page has R equals to 0, then we will simply replace it. So we will move like uh, this. Suppose if here R equals to 0, here R equals to 1, R equals to 1. So if here R equals to 0, replace it. Okay. If r equals to 1, give second chance. So if r equals to 1, then it is given second chance and the pointer moves ahead. Skip pages, move pointer ahead until it finds r equals to 0 again. So whenever it finds r equals to 0 for any page, it will replace it. Okay. So this is called clock because pointer rotates like clock, and why good? Because it is cheap approximation of LRU. And it is very popular in real OS. So 11 will be to 11 would be to add enhance second chance. So what does second chance do? This is second chance. Okay, so yeah, it is second chance of block algorithm. Adds modified bit. Now pages are classified using R bit and modified bit. So four classes 0, 0, 0, 1, 1, 0, 1, 1. So best victim property would be 200. That is, it is not modified recently and it is not used recently. So OS prefers 00 because not recently used, clean page. That is, it is not modified, no disk write needed. And worst would be 211. That is, it can never be removed. Okay. Why these algorithms exist? So the whole goal is to reduce the page fault because page faults are extremely expensive. So the final uh, intuition hierarchy. Optimal is the best. Practical? No. T4 simple, weak. NRU very good, expensive. Yeah, NRU is expensive. Clock very practical. Practical, yes. This is the quality of this. Enhanced plot better practical, widely used. So this one is widely used. The most important conceptual takeaway, the entire memory management story is CPU wants data. If page is in RAM fast, else page fault, disk access becomes bottleneck. So OS tries to keep important pages in RAM. Okay. This is the final conceptual takeaway. And page replacement algorithms decide which page are important enough to keep. Then, yeah, this is the final concept of virtual memory, crashing plus locality. This one is actually most important OS ideas. Okay, it has been saying this statement for a lot time. Everything till now, how paging works, but this topic asks when does paging becomes bad? The bad condition is thrashing. We have seen the thrashing term before. Definition: CPU spends more time handling page fault than executing program. Yeah, it is bad. If CPU spends more time handling page fault, bringing pages from disk to RAM, then it is obviously bad. Because it means RAM is too small, pages constantly swapped between RAM and disk, page faults explode, CPU waits for disk, performance collapses. And why it is bad? Remember, CPU cache, yeah, again, it is all talking about speed. The graph first image, degree of multi-programming, CPU utilization. Okay, so let's see the graph. If that graph, yeah, so I think this is percentage of CPU utilization and degree of multi-programming. So we see here percentage of UP, here we see the degree of multi-programming is high, but CPU utilization is 0. And this point is deadlock. So thrashing is the point just before deadlock. You see here degree of multi-programming. Initially more process, more CPU utilization. CPU utilization increases. Why? Because if one process waits, another can run. Okay, so this is good. But after some point, too many processes share RAM. Each gets very few frames. Then page fault explode. Now CPU mostly waits for disk. So utilization drops. That drop is reason is thrashing. So the most important core idea, more processes not equals to always better. After a limit, system collapses. And the main cause of thrashing is too few frames plus too many processes. Okay, so this is the main cause of thrashing. Each process needs some minimum working memory. If not available, continuous swapping happens. Okay. And the detection of thrashing. Operating system observes low CPU utilization, very high page fault rate. disk heavily busy. So this combination means system is thrashing. Okay. So detection of thrashing, operating system observes low CPU. Okay, so whenever operating system observes low CPU utilization, very high for page fault rate, disk heavily busy, so it means system is thrashing. Similar thing we have seen in the detection of deadlock. Okay. So recovery is what OS should do, not add more processes, instead reduce degree of multiple, means suspend block some processes. Then remaining process get more fame and page fault reduces. So the page size effect very important. In smaller page size, example 1 KB, advantage less internal fragmentation. But too many pages, huge page table, more page fault possible. Larger page size, advantage fewer page table, smaller page table, fewer pages, but smaller page tables and fewer fault, but more internal fragmentation. So page size is a trade-off. Okay. Now the most important part, locality or program structure. This explains why some code run fast and some slow. So the matrix example this, assume row major. Okay, so row major storage, page size equals to 128 bytes. Okay. Memory invert. In C++ arrays are stored row by rows. Okay. Yeah. Are in adjacent memory. We know that matrix arrays are stored row by row, not columns. This is called row major order. So program one would be this. Notice carefully. Access pattern column wise. And why this is bad? Memory stored row wise, but access is column wise. So access jumps across pages repeatedly. Think visually. You access. These are not adjacent in RAM. Each may belong to different page. Okay, so we see that suppose A1 is one array and it is in one page. A2 is in separate page. So when we do this, so these are not adjacent in RAM. So by column it means going this. So first, second, third, not this. Okay. So this is a thing that access wise column is bad than row wise. These are not adjacent in RAM, so each may belong to different page. Also, we see that for this program it happens, we usually write I comma Aij so that we can access faster, or also we can access row wise instead of column wise. Okay, this is accessing column wise, but suppose this program, this is our user program, now access is row wide. Why this is good? Because memory itself is stored row wise. So once page is loaded, many nearby elements also available. Okay. So this is a spatial locality which results in far fewer page fault. So many modern performance heavily depends on locality of reference. So we have talked about it. So the types of locality, temporal locality, recently used data like D to use again. Okay. So sum plus equals to x variable reused repeatedly, and spatial locality, nearby memory likely accessed from. So arrays are perfect example. Why caches work before? Because programs usually have locality. Now what is this linked list versus array? Last image, arrays contiguous memory. Linked list nodes is scattered across memory, traverse and jumps everywhere. Word locality, more page fault. And arrays have less page fault because memory is contiguous. So important modern insight. This topic is why arrays are often faster than linked list. Cache friendly code matters. Loop ordering matters. So this is the whole memory management thing. The whole story is how OS gives illusion of huge fast memory using a small slow RAM plus disk efficiently. Okay. Like suppose you have a game of 500, not 500, but at least 150 GB. Like I have RDR2 in this PC. If you will see, yeah, there is RDR2. I don't know. It is in Steam, I guess. I have not made the icon. I guess I have. So yeah, I have 150 GB of RDR2 game, suppose, and my RAM is only like 16 GB. So the game size is 10x more than the RAM, but still the game loads properly. Even after we know that the whole game needs to be loaded in RAM before running. So this is done using the paging concept. Okay, so this is why paging is very important. Now we have completed our memory management. All what is left is uh, we have talked about what TNB hit. Okay, so we have talked about this part, segmentation. Yeah, so we need to talk about the segmentation now. We will make notes of segmentation, but before that, let's try to read the Bernardi's anomaly. Okay, so Bernardi's anomaly is this. What is Bernardi's anomaly? So it is a counterintuitive phenomenon in computer operating system where giving more process more physical memory page frames actually increases the number of page faults. The anomaly specifically affects the FIFO. FIFO is a simple queue system when memory is full and a new page is to be loaded, the oldest page in memory is kicked out, regardless of how often it is used or if it will be needed again in the next step. So when you increase the number of frames, you change the exact timeline of when pages enter and leave the queue. In specific edge cases, this new timeline causes the algorithm to evict highly active pages right before they are needed, so resulting in cascade of extra code. Okay, so what does we understand? When we increase the number of frames, we change the exact timeline of when pages enter and leave the queue. So yeah, if we increase the number of frame given to one process, we change the timeline of one page's enter and when it's leave the queue. In specific edge cases, this new timeline causes the algorithm to evict highly active pages right before they are needed. Yeah, so I guess it is the same thing as I have talked about, like the classic proof. To prove this, computer scientist is this too much. Page sequence this, finished 9 faults. Current fault is 9. Frame count is 3. Yeah, so we see 3 frame counts. Basically, we can understand it by this. To prove this, computer scientist uses specific memory access request a reference string to show the, yeah, so a reference string we have seen. Requesting memory in exact order 3, 2, 1. So this is that 3, 2, then 1, then 0. So how 0 will be placed? So 0 will be placed like this. Now 3. So yeah, so 3 will come, replace it and it will go along. So now 2, now 4, now again 3. So as 3 was already present here, you can see here we are 2 is not present in this. So when 2 was called, it was added in this. So page faults are 1, 2, 3, 4, 5, 6, 7, 8 and 9. So 9 page fault. Yeah. So 3 we see 3, 2, 4, 3 is already there, so no page fault. 2 is already there, so no page fault. Now 1 is not there, so page fault. 0 is not there, so page fault. So 4 is there, so no page fault. Okay. Now suppose we increase the frame count to 5. So 3, 3, 2, 3, 2, 1. Yeah, then here we see page fault is less. Uh, Increasing page fault was said that increasing page fault does this. Okay, so let's see. Okay, so for 3, okay, so we have increased it too much. Let's do it for 4 page fault. Okay, So 3, 3, 2, 3, 2, 1, 0. Then 3 is accessed and 3, 2 is called. Then 4, 3, 2. Yeah, really, here we see 10 page fault. 3, 2, 1, 0. So 3 is called, then 2 is called. So it is already there, so no changes. Now when 4 is called, it does replace this. So when 3 is, yeah, so for the same thing, having larger page fault really increases the fault. This is a very good example. I will stick it in my notes. Okay, so yeah, I had not thought about this. The system keeps cycling out old pages, but the final few requests happen to be still in memory when needed. With an extra sort, the timeline shift. When 4 is requested, the system kicks out 3, but 3 is needed immediately after causing a fault. This domino effect ruins the, yeah, the same thing I have explained. This is the same thing, what is Benedi's anomaly. Okay, so I guess I have explained the correct thing. And yeah, so this is nice. We just have to make the notes now. Okay, so let's make notes after 8 minutes break. Yeah, so the break went a little longer than expected, but it's fine. Let's get back to the work. So yeah, after multi-level paging was our last solution for paging. After this, we will study about the segmentation. Okay, I guess we need to go more down. Okay, so we will study the segmentation thing from now. We have studied, we will just make the notes of it. So segmentation. This is the best explanation of segmentation. Like could be what happened to my voice. Okay, so yeah, this is segmentation. Segment idea is also required. This is not required, we know the difference. We are just keeping the idea and intuition here. Okay, intuition is what basically required for all the terms here. Here the logical address would be. I guess I have wrote the logical and physical address opposite. Yeah, so I have written it opposite. This is the logical address and this will be the physical address. This is the whole thing. So the segment table will have here the S will be segment size. The problem with segmentation, segments are variable size, so I will problem again external segmentation. Due to variable sized pages, segments. Okay, solution segmented pages. So I guess I should write it in red only. Okay, segmented paging, paging inside segments. And A will be S P D. Why this happens? So we get logical organization from segmentation. No external segmentation from. Final topic would be memory. Now the third last topic is virtual memory. Okay. So yeah, this will be the first last topic. So before this, this is the core idea of virtual memory and paging. Okay. This can be directly asked. So for doing this, we need one more property in page table. So this is the whole thing. Here is the 4 pages part. So here we will have the 4 pages. This is the longest thing. Okay. So now 2 segments are remaining after this. Okay, so page font handling and demand paging performance. So page font should be highlighted. This is a important topic. Okay. This page font is very expensive. And why it is expensive? Because fetching process pages from this takes most of the time. Takes large amount of time, I should write. Large amount of time. Okay. Mhm. So the page fault services. Suppose process wants page one. Then we have talked about this thing. Okay. Now the definition of dirty page and clean page is also here. So the demand paging is also of two types. Okay. Demand paging is also of two types. What are those types? Now the EMAT is also here. So total average EMAT. Instead of weighted average, we should write this. Okay. Performance is always calculated in this. So performance okay. So yeah, memory plus demand paging, I think. Okay, so yeah, this is the whole thing. Important understanding. Very small page fault rate. Okay, so yeah, we know even a small page fault. So this is page fault rate. Time to fetch from this, not this, but this. Okay, no, even a small page fault causes destroys performance. Yeah, so now we will have total of four pages here, then two pages ahead. Those two are very easy. Okay, so these four are very important. Okay, so if RAM becomes full, which pages should I remove? So now we will study the page replacement algorithms. Mm. Okay, so So yeah, let's continue. Next, we create a reference statement. So what is the page reference statement? It is simply one of the which pages are requested over 20. So the concepts are now numbered, so it will be easy for me to even directly finish it. Okay. But really, let's do this. Page reference statement. Now the frame and kissing policy. Second, the kissing policy. We have studied it. Now page replacement algorithms. You will now maybe which maybe we identify concept now we can study and go done. So first would be P4. So what is P4? You know P4, okay. Do you know P4? Problem with P. Well, it's coming here. So what is the problem? Then a D and one D. And what is then a D and one D? Maybe we can return here. And then one D, move that. And we also have the little the best thing I think. Little the best thing. People has like thought progressing. And that's the start. It's sequence. Different capitals and frame counters three. So I will clear. I'm not preparing the Google. So generally this will not happen, but It happened in before. Okay. This is high before is considered bad. And Gennady anomaly here also we didn't understand. So which is Gennady anomaly. This is Gennady anomaly. Okay. And this is Gennady anomaly. Now, what is the next topic? Yes. We have seen the Gennady anomaly. Now the next algorithm will be optimal replacement. So second will be optimal replacement algorithm. Optimal replacement algorithm. So what does it mean? Do you know tool that will be used for the minimum that will be used for the yes. Similar technique, there is no data. So the next one will be low the value will be say new then value anomaly. So will be and then we may just indicate mechanically of that one. Indicate the government sales potential connectivity. This page you recently likely to use against them. When you use a stack algorithms, then one will be yeah, behavior diagrams. algorithm to be precise, but counted as algorithm. This algorithm concept. What is the concept for it? Now we are new counting algorithm. Yeah, so in our new, if it's these are also required. Order, you will be done. And now you and you will make me maybe use that counting algorithms. Okay, these are counting algorithms. Scenario approximation. Okay, so next will be scenario approximation. And approximation. Though scenario is very expensive, so operating system uses some approximation. Okay. Reference bits. If page is accessed, they will turn reference bits and periodically it resets in the period is resets R1 to R0 and this period is not. So this period is very important. So what is ID? ID are input. Now we include this. Channel. It's not aligned. Now between pointer will move around. Yes, so pointer will keep moving around and it will remove the pages if I touch. But even after this, it's not enough. You know, even in this, flowing. You know, How does this one? So it introduces one more bit which is a modified bit. And modified bit. The program is two modified bit and reference bit. The four patches are yes. So it means it means one one create engine modified in RAM. So inverting field. Uh, so figure complete. Okay. Four classes, motivate three and motivate 30. But in best testing priority will be to towards preference 0,0 because in the present previous screen page no write test, no list write to do that. One goal is to reduce page count. And this is the final MTOS. This type of thing is required at last to finally summarize why we studied all of this. Okay. You know, then we still have final topic left, which is tracing and locality. So what was tracing? More processors not equals to always better. Yeah, so I should say that we should summarize it. Let's do it using Gemini. Okay. It explains like awesome and also in less space. And also it, the interface is awesome, so it will be easy to that restrict. So if we like explain this, so yeah, we know lesson. Let's study it once more, and then it is generating the answer. So why this topic as to genders paging becomes bad. The bad condition of pairing. So if CPU spends more time handling page fault rather than executing programs, then it is bad and it is that's okay. So it is bad, obviously. So we also have that we can ask me on the next topic is flashing so directly. Yeah. So we will make it with the graph. Let's take the graph. This is the graph for the pricing. So this is like the awesome definition and everything of pricing. Okay. to like a good page, excessive page activity, very high page fault rate, low CPU utilization, these are the detection techniques. Okay. I guess it will not. Yeah. And page size spread out and look and pay for the price. This is really going to some. It doesn't need to do this, but still it does for the better explanation. Okay. That's why I know. When the system gets how programs get it, um, detect dictates execution speed. Okay, so simultaneous. So first is pressing. Snails paving brands. So let's write it. So X name then paving becomes bad. Okay. So vector memory allows restaurant programs landed in specific by constantly swapping pages of data between the timeline hard disk. The problem is we run too many procedures. Means the OS has to divide into different RAM frames among them. Eventually, processors doesn't have enough frames to keep activity. For that, the system enters a state called flattening. Process constantly asks for data that is in RAM and causing page one. The OS switches it. And this was 1,000 times more than RAM. Then CPU sits idle waiting for the disk to fetch data. It drops to zero leverage to access out 100% give you and the impact in the figure on that seven. XOS protection. Playing up random frames, so we make it suspend frames. Yeah. So how does it better? When we suspend blocks and procedures, playing up their random frames, make it suspend. So it knocks the heavy processors. Let's play this. Move this, not data, this and temporarily suspend or block some processes. This is the main thing. Is there anything else than this in pricing? So the main point of pricing, the main part of pricing and how to correct it. You can correct it by detection of pricing, reduce the degree of multi-programming. And page size is a thread. Reduce the degree of multi-programming, so suspend or blocking some process can improve it. Okay. So detection and recovery, the one algorithm that was used in Deadlock 2 is here works together as detection and recovery. One to else and recovery. Okay. So yeah, this is and the page size effect, the small page size. This is important. This is a general concept. Okay, so um, let's mark it 5 star. Small page size, advantage less written but too many pages, huge page table, more page font possible. Okay. Because if page tables are too many, then page font occurrence has more chance. Large page size, fewer pages is more internal fragmentation. Okay. So page size is spread out. Now, with this matrix example, I think it's not this one, in the other one, page size spread out. Let's explain this here also. Okay, so what is the page size trade-off? Let's read this. The OS has to decide how big a page of memory should be. Example 1 KB versus larger size. Small pages save space because data fits perfectly. Okay, less data and fragmentation. But the OS has to manage thousand. We also studied about the optimal page size before. Okay, so I don't think this is too much required, but that's pretty high. Okay, but OS has to manage thousands of tiny pages, creating a massive page table and using node page tables. Okay. Now, larger pages easier for the OS to track. The smaller page tables with fewer fonts, but if a process only needs one bit of memory, it still occupy a huge page, wasting the remaining space. Okay. So yeah, this was the thing. And now the final topic. This is the final topic, and we have already studied how to program to an exact same mathematical and widely different education of student. Now comes the more important topic because this is very important for interview purpose. Locality of reference. So we have studied an example also. Yeah. So this is the complete operating system goals for the revision. We have not solved any problem. We just studied it theoretically everything. But yeah, theoretically this was very good lesson. Even after removing the less important topic for interviews like files and disk management. Okay. So these are hardware internals not required for the software jobs. Okay. You can study it if you want. I think that you have not covered it in this lecture. And let's finalize this lecture. Thanks a lot for joining.